Imagine standing at the edge of time itself. The universe is young, barely 100 million years old. Around you, there are no galaxies, no planets, no familiar celestial structures. Only darkness and formless clouds of hydrogen and helium drift through the void. And then, something extraordinary happens. In the distance, a pinpoint of light appears, then another, and another. These are the very first stars igniting across the cosmos, born before galaxies themselves existed. Massive, brilliant, and unlike any stars we see today, these ancient luminaries transformed the universe from a dark, featureless expanse into the structured cosmos we recognize. They forged the first heavy elements in their cores, scattered them across space when they died, and laid the foundation for everything that followed, including us. Tonight, we journey back to witness these cosmic pioneers, the stars that were born before the first galaxies, the forgotten ancestors whose light shaped our universe in its infancy. Picture our universe at its beginning, not as we know it today with its brilliant stars, swirling galaxies, and planets teeming with life, but as a vast expanse of darkness and simplicity. What happened after the explosive birth of our cosmos in the Big Bang? The answer might surprise you. For nearly 380 years after the Big Bang, the universe was an opaque, superheated plasma, too hot and dense for light to travel freely. Then came an event astronomers call recombination. As the universe cooled below 3000 Kelvin, electrons combined with protons, forming the first neutral hydrogen atoms. Suddenly, photon particles of light could travel unimpeded for the first time. This moment released what we now observe as the cosmic microwave background radiation, the oldest light in our universe. But paradoxically, this also marked the beginning of darkness. Why? Because although light could now travel freely, there were no sources of new light, no stars had yet formed to illuminate the cosmos. And so began what astronomers poetically call the cosmic dark ages. For millions of years, perhaps as many as 100 million years, the universe drifted in darkness. Vast clouds of hydrogen and helium filled space, invisible to any observer who might have been there to witness it. The temperature continued dropping as space expanded, eventually reaching just a few degrees above absolute zero. Time passed. The universe grew. But in the darkness, subtle forces were at work. Tiny fluctuations in density, quantum ripples from the earliest moments after the Big Bang began to grow under gravity's patient hand. These minute differences, merely 1 part in 100, were the seeds of future structure. In regions where matter was just slightly denser than average, gravity pulled more material inward, slowly at first, then with increasing speed and significance. As these primordial hydrogen clouds grew denser, they began to collapse under their own weight. The gas grew warmer as gravitational energy converted to heat. These collapsing clouds, known as mini-halos, would eventually become the birthplaces of the first stars. But the physics of this early universe was fundamentally different from what we observe today. The gas was pristine, composed only of hydrogen, helium, and trace amounts of lithium. There were no heavier elements, which astronomers call metals, even though this term includes everything heavier than helium. No carbon, no oxygen, no iron elements we take for granted today. This absence of metals made cooling difficult. In today's universe, metals help gas clouds cool efficiently, allowing them to collapse more easily into stars. Without these cooling agents, primordial clouds needed to reach much higher densities and temperatures before collapse could begin in earnest. Computer simulations show us that these pure hydrogen clouds needed to reach masses of about 100 times that of our Sun before they could fragment and form individual stars. These massive gas reservoirs became the first stellar nurseries in cosmic history. Inside these dense cocoons of primordial gas, temperature and pressure continued rising. At their cores, hydrogen atoms collided with increasing energy. The density grew so extreme that the hydrogen began to ionize again, with electrons being stripped from their atoms. This electrically charged plasma continued heating until it reached temperatures of millions of degrees. And then, something magical happened. The temperature and pressure at the center of these gas clouds became so intense that hydrogen nuclei could overcome their natural electromagnetic repulsion. They fused together, releasing enormous energy in the process. Nuclear fusion, the same process that powers our Sun today, had begun for the first time in cosmic history. This moment, occurring somewhere between 100 and 200 million years after the Big Bang, marked the birth of the very first star population 3 stars, as astronomers would later classify them. The long cosmic dark ages were coming to an end. But these first stars were unlike anything we see in our night sky today. Born from pristine gas, uncontaminated by previous generations of stars, they formed under unique conditions that would never again exist in our universe. They were giantsome with masses, perhaps 300 times greater than our Sun. Their surfaces blazed at temperatures exceeding 100 Kelvin, compared to our Sun's modest 800 Kelvin. These stellar behemoths produced energy at phenomenal rates. A single first-generation star might shine with the brightness of an entire modern galaxy. Their intense ultraviolet radiation began to interact with the surrounding hydrogen gas, ionizing it and creating bubbles of hot plasma around each star. These ionization bubbles were the first structures to interrupt the uniform darkness of the early universe. As they expanded outward from each newborn star, they began to encounter and merge with bubbles from neighboring stars. This process, the epoch of reionization, would eventually transform the entire universe back into an ionized state, but in a completely different configuration than before recombination. The first stars didn't form everywhere at once. They appeared first in the densest regions where gravity had most effectively gathered gas. These regions would eventually become the cores of the first protogalaxies. But for a brief and remarkable period in cosmic history, stars existed without galaxies to contain them. These stars burned with furious intensity, consuming their hydrogen fuel at prodigious rates. Their enormous size and temperature meant they evolved quickly, living for perhaps only 2 to 3 million years compared to the billions of years that stars like our Sun exist. In their cores, nuclear fusion quickly progressed beyond hydrogen, synthesizing helium, then carbon, oxygen, and other elements. For the first time in the universe's history, atoms heavier than lithium were being created. Every carbon atom in our bodies, every oxygen molecule we breathe, every calcium atom in our bones had its origin in stellar cores. But these first-generation stars were forging these elements for the very first time. As these massive stars approached the end of their brief lives, their cores manufactured even heavier elements: silicon, sulfur, and eventually iron. But iron fusion consumes rather than produces energy, and this marked the beginning of the end. Their cores, no longer supported by fusion energy, collapsed catastrophically. The outer layers fell inward, rebounded off the dense core, and were ejected outward in cataclysmic explosion supernovae of unprecedented power. These explosions, far more energetic than typical supernovae we observe today, scattered the newly forged elements across space, enriching the surrounding gas clouds. Some of these first stars, particularly the most massive ones, might have ended their lives in even more dramatic fashion as pair instability supernovae. In these extraordinary events, the core becomes so hot that energy converts directly into matter and antimatter, causing the star to become unstable and explode completely, leaving no remnant behind. Others collapse directly into black holes, the first black holes in cosmic history. These stellar mass black holes would later serve as seeds for the supermassive black holes we now find at the centers of galaxies, including our own Milky Way. The deaths of the first stars forever changed the universe. The pristine condition of the cosmos, composed solely of hydrogen and helium, could never be restored. Each subsequent generation of stars would form from gas already enriched with metals from previous stellar deaths. This changed the fundamental physics of star formation, allowing smaller, longer-lived stars to form stars like our Sun. As we look up at our night sky, we see none of these first stars. They all died billions of years before our Earth formed. But their legacy surrounds use in the chemical composition of our planet, in the structure of our galaxy, and indeed, in our own bodies. The Dark Ages ended not with a sudden flash, but with a gradual cosmic dawn as more and more first-generation stars ignited across the expanding universe. Their light began traveling outward, some of it still rushing through space today, though now shifted to wavelengths far beyond what our eyes can see. Astronomers hope that the next generation of telescopes might detect the collective glow from these first stars, or perhaps observe their spectacular deaths as gamma-ray bursts visible across cosmic time. For now, we rely on sophisticated computer simulations and indirect evidence to understand this crucial chapter in our universe's history. The stars that ended the cosmic dark ages were the pioneers that transformed a simple, dark universe of hydrogen and helium into the complex cosmos we inhabit. They were the alchemists that created the elements essential for planets and life, and though they lived and died long before galaxies formed around their remnants, their influence shaped everything that followed. How does a star form from nothing but hydrogen and helium? In our universe today, when we observe stellar nurseries in the Milky Way, we see complex interactions between gas clouds enriched with metals, magnetic fields, and the influence of nearby stars. But the first stars emerged from a dramatically different environment tone without any of these familiar factors. Let's journey back to that primordial universe, roughly 100 to 200 million years after the Big Bang. Space had cooled enough for matter to dominate over radiation, and microscopic density fluctuations, quantum echoes from the universe's first moment, had slowly grown under gravity's influence. These slight variations in density would determine where matter would eventually concentrate and where it would thin out. In regions where matter density was just slightly higher than average, gravity began its patient work. Hydrogen and helium atoms, drawn by this gentle gravitational pull, started flowing inward. The process was achingly slow at first. With only hydrogen and helium present, the gas couldn't cool efficiently. In today's universe, molecules and dust particles help radiating away heat, allowing clouds to collapse more readily. But without these cooling agents, primordial gas needed to reach much higher densities before collapse could accelerate. As these vast clouds of hydrogen and helium, which astronomers call mini-halos, grew more compact, something remarkable happened. At certain densities, hydrogen atoms began to pair up, forming molecular hydrogen, H2s. This simple molecule, rare in the early universe, proved crucial. Molecular hydrogen could rotate and vibrate, absorbing and emitting energy in ways that atomic hydrogen could not. This allowed the gas cloud to cool more efficiently, accelerating its collapse. Computer simulations reveal that these primordial clouds eventually formed structures resembling vast, ghostly filamenta, cosmic web of matter stretching across the expanding universe. At the intersections of these filaments, where gas could flow in from multiple directions, the densest clouds formed. These became the cradles of the first stars. As a cloud collapsed inward, its central regions became increasingly hot and dense. Conservation of angular momentum, the same principle that makes figure skaters spin faster when they pull in their arms, caused the cloud to rotate faster as it shrank. This rotation prevented complete collapse, flattening the cloud into a spinning disk with a dense central region. At the center of this disk, pressure and temperature climbed relentlessly. When the temperature reached about 10 million Kelvin and the density climbed to values almost unimaginable, hundreds of grams per cubic centimeter, the conditions for nuclear fusion were finally met. Hydrogen nuclei could now overcome their mutual repulsion and fuse together, releasing tremendous energy in the process. This moment marked the birth of a star, the ignition of the first self-sustaining fusion reactor in cosmic history. Light pushed outward, counterbalancing gravity's inward pull. A delicate balance was struck. The first star was born. But these first stars, called population 3 stars by astronomers, were fundamentally different from stars we see today. Their pristine composition, lacking metals that absorb radiation, meant they could grow to truly massive sizes. While typical stars today might have 8 to 100 times the Sun's mass, the first stars could reach 300 or even 500 solar masses. These were true stellar giants, unlike anything in our contemporary universe. Their enormous mass meant they burned hot and bright. A typical first star might have had a surface temperature of 100 Kelvin, more than 17 times hotter than our Sun. These cosmic beacons shone with ultraviolet light, so intense that a single star could outshine an entire dwarf galaxy of today's stars. Their formation also differed fundamentally from modern star formation. Today, a collapsing gas cloud typically fragments into many smaller clumps, each becoming a separate star. This creates star clusters with hundreds or thousands of stars of various masses. But simulations suggest the first gas clouds might have formed just one or a few massive stars, rather than clusters of smaller ones. Why this difference? Again, it comes down to cooling efficiency. Without metals, the gas couldn't cool and fragment as readily. Instead of forming many smaller stars, the available matter coalesced into fewer, more massive objects. This preference for creating massive stars rather than numerous smaller ones is called a top-heavy initial mass function in astronomical terms. This had profound implications for the universe's development. Massive stars burn through their fuel quickly and die young. A star with 200 times the Sun's mass might live just 2 million years, compared to our Sun's expected 10 billion-year lifespan. This meant the first generation of stars lived brief, brilliant lives. The intense radiation pouring from these newborn giants immediately began transforming their surroundings. Ultraviolet photons ionized nearby hydrogen, creating expanding bubbles of hot plasma around each star. These ionized regions, called high II regions, were the first structures to interrupt the uniformity of the dark cosmos. As these stars formed across the universe, they didn't appear everywhere simultaneously. They ignited first in the densest regions, the peaks of those initial quantum fluctuations that had grown under gravity's influence. These regions would eventually become the cores of the first proto-galaxies. But for a brief and remarkable period, stars existed as isolated beacons in a universe that had not yet developed larger cosmic structures. The birth process of these first stars was likely violent and dynamic. As gas continued falling onto the protostar, it formed accretion disks that channeled matter toward the developing stellar core. These disks may have been unstable, fragmenting into companion protostars or gas clumps that were eventually consumed by the primary star. Simulations suggest some of these early stars may have rotated at tremendous speeds, perhaps approaching 50% of their breakup velocity, the speed at which centrifugal force would tear them apart. This rapid rotation flattened their shape and may have triggered complex mixing processes in their interiors, affecting their evolution and eventual fate. As these pioneering stars stabilized, nuclear fusion in their cores began producing energy at phenomenal rates. The primary fusion process, the proton-proton chain that also powers our Sun, converts hydrogen into helium. But because of their extreme temperatures, these stars could efficiently use the CNO cycle as well, a more temperature-sensitive fusion process that becomes dominant in massive stars. An interesting paradox of these first stars is that despite lacking metals like carbon, nitrogen, and oxygen at their birth, they could produce small amounts of these elements through fusion processes within minutes of ignition. These newly created elements then catalyzed further reactions, allowing the star to establish stable energy production. The immense pressure and temperature inside these stellar giants created conditions where fusion could progress rapidly to create heavier elements. While our Sun will never be hot enough to fuse elements heavier than helium in significant quantities, these first stars quickly built up carbon, oxygen, neon, magnesium, and eventually silicon in their cores. As they evolved, these stars developed a distinctive structure, fusion-powered core, surrounded by layers where different elements were being synthesized, encased in a vast envelope of original hydrogen. Their enormous size meant gravity at their surfaces was relatively weak, despite their great mass. This allowed stellar wind streams of particles driven by radiation pressure to flow outward from their surfaces. However, these winds were likely weaker than those from massive stars today. Without metals, which provide many of the electrons that absorb photons and drive winds, even these intensely luminous stars had difficulty pushing material away from their surfaces. This meant they retained most of their mass throughout their brief lives, making their eventual deaths all the more spectacular. The landscape of the universe during this era would have appeared alien to our eyes. Imagine vast, dark spaces punctuated by isolated, intensely bright pinpoints of blue-white light. No galaxies yet existed to contain these stars, just individual stellar giants floating in the cosmic void, each surrounded by its own growing bubble of ionized gas. These ionized bubbles continued expanding throughout each star's lifetime. In regions where stars formed in relative proximity to each other, these bubbles eventually began to overlap and merge. This process marked the beginning of what astronomers call the epoch of reionization, the transformation of the neutral universe back into an ionized state, but with structure rather than uniformity. As more stars formed, their collective light began to fill the universe. The cosmic dawn had begun. After millions of years of darkness following the release of the cosmic microwave background, new sources of light were illuminating the cosmos. This light traveled outward, some of it still rushing through space today, though now redshifted far beyond the visible spectrum due to the universe's expansion. When we observe the most distant galaxies with our most powerful telescopes, we're seeing light that has traveled for over 13 billion years light, that originated not long after these first stars began to shine. The birth of the first stars represents one of the most significant transitions in cosmic history, from simplicity to complexity, from darkness to light. They were the universe's first alchemists, forging new elements in their cores. They were the first sources of light after the long cosmic dark age. And they were the precursors to all the cosmic structures we see today. Their formation required a delicate dance between opposing forces: gravity, pulling inward, pressure, pushing outward, rotation providing support, and molecular hydrogen enabling crucial cooling. When these factors balanced just right, a star was born. When this process repeated across the primordial universe, the course of cosmic history changed forever. Perhaps most remarkably, the physics that governed the birth of these first stars connects directly to our own existence. The elements forged in their cores and scattered by their explosions would eventually find their way into later generations of stars, into planets, and ultimately into living beings. When we study the first stars, we study our own cosmic origins. The story of these stellar pioneers is written not just in sophisticated computer simulations or theoretical models. It's written in the chemical composition of the oldest stars still surviving in our galaxy's halo. It's encoded in the pattern of temperature fluctuations in the cosmic microwave background. And it may soon be directly observable with next-generation telescopes designed specifically to peer back to the universe's first billion years. As we stand on Earth today, looking up at our star-filled sky, it's humbling to remember that every star we see belongs to a much later generation than these first luminaries. The pioneers that first lit the cosmos have long since burned out. But their legacy surrounds us in every element heavier than lithium, in the very structure of our galaxy, and in the continuing story of stellar birth and death that characterizes our dynamic universe. The birth of the first stars wasn't just a beginning, it was a transition that transformed everything that followed. They were born from darkness and simplicity, but they gave rise to light and complexity. They were the universe's first steps toward the rich cosmic tapestry we inhabit today. As we continue to study these ancient stellar pioneers, we gain deeper insights not just into astrophysics but into our own cosmic heritage. Every atom in your body heavier than lithium was created inside a star. And the very first of those star-forged atoms came from these primordial giants that illuminated the universe for the first time. What makes Population 3 stars so extraordinary compared to the stars we see in our night sky? To understand their uniqueness, we need to explore how astronomers classify stellar populations and why these first stars stand apart from all others. Astronomers use a somewhat counterintuitive naming system for stellar populations. The stars we see in our galaxy today, including our Sunari, called Population 1 stars. They're relatively young and metal-rich. Older, metal-poor stars found primarily in globular clusters, and our galaxy's halo are called Population 2. The first stars, those ancient giants formed from pristine hydrogen and helium, are designated Population 3, a classification created before any such stars had been directly observed. This backward numbering system reflects the historical development of our understanding. Astronomers categorized the stars they could observe before theorizing about the ones that must have existed before them. And Population 3 stars truly did exist in a category all their own. Imagine a star 100 to 300 times more massive than our Sun. Its surface blazes at temperatures exceeding 100 Kelvin compared to our Sun's modest 800 Kelvin. It shines with ultraviolet light so intense that a single star could outshine an entire dwarf galaxy of today's stars. Its huge mass means gravity compresses its core to extraordinary densities and temperatures, accelerating nuclear fusion to a frenzied pace. This was a typical Population 3 star. These stellar giants were defined by several key characteristics that set them apart from all subsequent stellar populations. First and most fundamentally, they formed from pristine gas matter that had never been processed inside a star before. Their composition was nearly pure hydrogen and helium, with just trace amounts of lithium and beryllium created during the Big Bang. This lack of heavier elements, which astronomers call metals, profoundly affected their formation, structure, and evolution. Without metals to help radiate away heat, gas clouds couldn't cool efficiently. This meant they needed to reach higher densities before collapsing, leading to the formation of larger stars rather than clusters of smaller ones. The absence of metals also meant these stars had different opacity. They were more transparent to their own radiation, allowing energy to flow outward more freely. This transparency had a dramatic effect on their size. A population 3 star might have been 2 to 3 times larger in diameter than a modern star of equivalent mass. Their lower opacity also meant reduced radiation pressure in their outer layers, allowing them to retain more of their mass despite their intense luminosity. Inside these stars, nuclear fusion proceeded at astonishing rates. Their cores reached temperatures of 50 million Kelvin, or more significantly hotter than our Sun's 15 million Kelvin core. At these temperatures, fusion reactions occurred much more rapidly and efficiently. A population 3 star with 200 times the Sun's mass might generate energy at a rate millions of times greater than our Sun. But this accelerated energy production came at a cost: a drastically shortened lifespan. While our Sun will shine for about 10 billion years, these first stellar giants exhausted their nuclear fuel in just 2 to 3 million years. They lived fast and died young, burning brilliantly for what amounts to a cosmic eye blink. During their brief lives, these stars evolved differently from stars we observe today. Modern massive stars experience significant mass loss through stellar wind streams of particles driven from their surfaces by radiation pressure. But population 3 stars, lacking metals that provide electrons to absorb and re-emit radiation, likely had much weaker winds despite their enormous luminosity. This reduced mass loss had profound implications for their evolution and final fate. Without shedding significant mass during their lives, they retained most of their initial bulk, making their eventual deaths all the more catastrophic. As they aged, these stars developed a distinctive internal Structurian onion-like arrangement of concentric fusion shells. In the core, initial hydrogen fusion created helium. When hydrogen in the core was exhausted, the core contracted and heated until helium could fuse into carbon. This process repeated, with each fusion stage producing heavier elements: carbon fused to oxygen, neon, magnesium, and eventually silicon and sulfur. Unlike our Sun, which will never be hot enough to fuse elements heavier than helium, these stellar behemoths could forge elements all the way up to iron in their cores. This marked them as cosmic alchemists, the first factories for creating elements heavier than lithium in the universe. Their enormous mass also caused significant mixing within their interiors. Rotational forces and convection currents may have brought newly synthesized elements from the core up toward the surface, while drawing fresh hydrogen down to the core. This mixing enhanced their fusion efficiency and may have even affected their surface composition over time. As these stars approached the end of their lives, the pace of fusion accelerated dramatically. While the hydrogen burning phase might last a couple of million years, each subsequent fusion stage occurred more rapidly than the last. The final silicon burning phase might last mere days before the star's core filled with iron element that consumes rather than produces energy when fused. This marked the beginning of the end. With no energy source to counter gravity's relentless pull, the core collapsed catastrophically. What happened next depended on the star's exact mass and rotation. For stars between roughly 140 and 260 solar masses, theory predicts a particularly dramatic fate called a pair instability supernova. In these extraordinary events, core temperatures become so extreme that energy spontaneously converts into matter and antimatter pairs. This sudden energy conversion reduces pressure support, causing the star to partially collapse. The collapse raises the temperature further, triggering runaway fusion that completely disrupts the star, leaving no remnant behind, just an expanding shell of newly forged elements. For somewhat less massive population 3 stars, perhaps 40 to 140 solar masses, the end likely came as energetic supernovae that ejected much of the star's mass while leaving behind black holes. These would have been the first stellar mass black holes in cosmic history, objects that may have later served as seeds for the supermassive black holes we now find at the centers of galaxies. The very largest population 3 stars, those exceeding 260 solar masses, might have collapsed directly into black holes without a supernova explosion, through a process called photodisintegration. In their cores, temperatures became so extreme that photons carried enough energy to break apart atomic nuclei, reducing pressure support and allowing gravity to win the final battle. These various explosive deaths forever changed the universe's composition. The newly forged elements carbon, oxygen, nitrogen, silicon, iron, and more were scattered across space, enriching the surrounding gas. This chemically enriched material would later be incorporated into the next generation of stars, altering their properties and enabling the formation of planets and, eventually, life. The supernovae of population 3 stars were likely more energetic than typical supernovae we observe today. A pair instability supernova might release 10 times more energy than a typical core collapse supernova. These explosions would have been visible across vast cosmic distances, briefly outshining entire galaxies. As their light and material spread outward, these dying stars helped shape the emerging cosmic structure. Their radiation ionized surrounding gas, creating expanding bubbles of hot plasma. Their explosions triggered shock waves that compressed nearby gas clouds, potentially stimulating the formation of new stars. And their heavy elements changed the cooling properties of gas, allowing subsequent generations of stars to form with different characteristics. But despite their profound importance in cosmic history, no population 3 star remains visible today. They all died billions of years before our own solar system formed. Their direct observation remains one of astronomy's greatest challenges. The intense ultraviolet light from these first stars has been traveling through space for over 13 billion years. In that time, the universe's expansion has stretched these photons, shifting them to much longer wavelengths from ultraviolet to infrared or even radio waves. This redshifted light is incredibly faint by the time it reaches Earth, making direct detection extremely difficult. Instead, astronomers search for indirect evidence of these first stellar giants. One approach involves looking for their supernovae. The explosive death of a population 3 star would produce a distinctive spectral signature, potentially detectable by sensitive infrared telescopes, like the James Webb Space Telescope. These pair instability supernovae would be distinguished by their unusual brightness and the particular mix of elements in their ejecta. Another approach focuses on finding the second generation of stars, those that formed from gas enriched by the first supernovae. These population 2 stars would carry chemical signatures of specific nuclear processes that occurred in the first stars. Some ancient, low-mass stars in our galaxy's halo may preserve these signatures like cosmic fossils. Computer simulations also help us understand these elusive objects. By modeling the physics of the early universe and following the collapse of primordial gas clouds, researchers can predict the properties of the first stars and how they affected their surroundings. These simulations suggest population 3 stars likely formed in isolation or in small groups, rather than in the large clusters typical of star formation today. The legacy of population 3 stars surrounds us. The carbon in our bodies, the oxygen we breathe, the silicon in Earth's crust, all these elements were first created inside these ancient stellar furnaces. When we look at the structure of galaxies, the distribution of matter across cosmic scales, or the chemical evolution of the universe, we see their influence. These first stars also played a crucial role in cosmic reionization, the process that transformed the neutral hydrogen of the early universe back into a plasma. Their intense ultraviolet radiation stripped electrons from hydrogen atoms, creating expanding bubbles of ionized gas. As these bubbles grew and merged, they fundamentally changed the universe's physical state, allowing light to travel more freely and altering how matter would collapse to form future cosmic structures. Population 3 stars may have also influenced the formation and growth of the first black holes. When these massive stars died, some left behind black holes with tens or hundreds of solar masses. These objects could have served as seeds for the supermassive black holes that now reside at the centers of galaxies. By accreting gas and merging with other black holes, these stellar remnants might have grown into the cosmic behemoths we observe today. Some theoretical models suggest a small number of population 3 stars might have had masses low enough, perhaps 0.8 solar masses or less, to survive until the present day. If such stars exist, they would be among the oldest objects in the universe, providing direct windows into the earliest stages of cosmic chemical evolution. However, Despite dedicated searches, no confirmed population 3 star has yet been found. The study of population 3 stars connects many fields of physics, nuclear physics, quantum mechanics, general relativity, fluid dynamics, and more. Understanding their formation, evolution, and deaths requires modeling complex processes across vast ranges of scale, from the subatomic particles involved in fusion reactions to the cosmological structures they helped shape. As our observational capabilities improve, we edge closer to glimpsing the direct evidence of these first stars. The James Webb Space Telescope, with its unprecedented infrared sensitivity, may detect the collective glow from early population 3 stars or observe their supernovae. Future radio telescopes might detect the signature of neutral hydrogen absorption against the background of the first luminous objects, what astronomers call the 21-centimeter forest. But even without direct observation, we know these stars existed. Their presence is necessary to explain the universe we observe to date: chemical composition, its ionization state, its structure. They left an indelible mark on cosmic history, transforming the simple, dark, early universe into the complex, luminous cosmos we inhabit. Population 3 stars were cosmic pioneers, the first alchemists, the original light bringers. They burned briefly but brilliantly, forever changing the universe in their wake. Though they vanished long ago, their legacy continues in every element heavier than lithium, in the structure of galaxies, and indeed, in our own existence. Without them, the universe as we know it and we ourselves could not exist. What happens when the first lights turn on in a universe that has known only darkness? For millions of years after the Big Bang, the cosmos existed in what astronomers call the cosmic dark ages. No stars, no galaxies, no sources of new light, just cooling, expanding darkness filled with neutral hydrogen and helium. Then came the first stars, and with them, a transformation so profound it would forever alter the course of cosmic evolution. When population 3 stars ignited across the primordial universe, they didn't just illuminate the darkness, they fundamentally changed the physics governing cosmic structure. Their intense radiation, particularly in ultraviolet wavelengths, began interacting with the surrounding neutral hydrogen gas in ways that would reshape the cosmos. The most immediate effect was ionization. Ultraviolet photons streaming from these stellar giants carried enough energy to strip electrons from hydrogen atoms, converting neutral gas into a plasma of free electrons and protons. Around each star, a bubble of ionized hydrogen formed what astronomers call an HII region, with the Roman numeral 2 indicating the ionization state of hydrogen. These ionization bubbles expanded outward at nearly the speed of light, creating spheres of hot plasma that grew larger every day. In regions where multiple stars had formed relatively close to each other, these bubbles eventually began to overlap and merge, creating larger, ionized regions. This process, the ionization of the neutral universe by the first sources of light, is known as cosmic reionization. It represents one of the last major phase transitions our universe has undergone, and one of the most significant chapters in cosmic history. Before reionization, the universe was opaque to ultraviolet light. Neutral hydrogen efficiently absorbs certain wavelengths, preventing them from traveling freely through space. But as more hydrogen became ionized, the universe grew increasingly transparent. Light could travel farther before being absorbed, allowing the first stars to influence more distant regions of space. This growing transparency had profound implications for subsequent cosmic evolution. Ionized gas has very different physical properties than neutral gas. It responds differently to radiation pressure, interacts differently with magnetic fields, and most importantly, cools and collapses through different mechanisms. The temperature of the affected gas also changed dramatically. While neutral hydrogen in the early universe had cooled to just a few degrees above absolute zero, newly ionized regions were heated to temperatures of 10,0 Kelvin or more. This heating counteracted gravity's pull in those regions, temporarily suppressing further star formation in already ionized pockets of gas. However, at the boundaries between ionized bubbles and neutral regions, the interaction created shock fronts that could compress neutral gas, potentially triggering new collapse and star formation. These complex feedback mechanisms, both positive and negative, created a constantly evolving landscape of gas dynamics in the early universe. The first stars didn't just affect hydrogen through ionization. Their intense radiation also influenced more complex chemistry. Ultraviolet photons could dissociate molecular hydrogen, H2s, which had been a crucial cooling agent, enabling the formation of the first stars themselves. This destruction of molecular hydrogen could temporarily suppress further star formation in affected regions. At the same time, the growing population of free electrons from ionized regions actually catalyzed the formation of molecular hydrogen through different pathways. These competing processes created a complex network of feedback that influenced where and when subsequent stars could form. The light from the first stars also began interacting with the small amount of dust that had been produced in their interiors and expelled through stellar winds. This dust, while much less abundant than in today's universe, could absorb ultraviolet photons and re-emit them as infrared radiation. This process not only reshaped the spectral energy distribution of light traveling through the cosmos, but also exerted radiation pressure on surrounding gas. As reionization progressed, the topology of ionized regions evolved in fascinating ways. Initially, ionized bubbles were isolated spheres around individual stars, or small groups of stars. As more stars formed, and these bubbles expanded, they began merging into larger, irregularly shaped ionized regions. Eventually, the topology inverted. Instead of isolated bubbles of ionized gas in a neutral medium, there were isolated pockets of neutral gas in an increasingly ionized medium. This topological inversion marked a critical point in the reionization process. The transition from mostly neutral to mostly ionized didn't occur uniformly across the universe. It proceeded faster in denser regions where more stars had formed, creating a patchwork of ionized and neutral zones that evolved over hundreds of millions of years. Computer simulations suggest that reionization was likely completed sometime between 500 million and 1 billion years after the Big Bang. By that point, virtually all hydrogen in the intergalactic medium had been ionized, and the universe had become transparent to ultraviolet lighter condition that persists to the present day. The effects of reionization are visible to astronomers studying the early universe. When we observe distant quasars' brilliant beacons, powered by supermassive black holes there, light passes through the intergalactic medium on its way to our telescopes. This creates absorption features that reveal the ionization state of hydrogen at different distances and times. These observations help constrain when reionization occurred and how quickly it progressed. But the light from the first stars did more than ionize gas. It also began affecting the dynamics of matter on larger scales. Radiation pressure from these intense sources pushed against surrounding gas, creating voids and channels in the cosmic gas distribution. This radiation-driven feedback helped shape the emerging cosmic web, the network of filaments, sheets, and voids that would eventually characterize the large-scale structure of our universe. The photons streaming from the first stars also carried momentum, and as they interacted with gas and dust, they transferred this momentum, creating radiation pressure. While individual photons carry minimal momentum, the tremendous number of photons emitted by these brilliant stars created significant cumulative effects, particularly on dust grains that could absorb light efficiently. This radiation pressure helped clear cavities around star-forming regions, potentially regulating further star formation through negative feedback. In some cases, radiation pressure may have been strong enough to expel gas from small protogalaxies entirely, delaying further star formation until more mass could be accumulated through gravitational attraction. Beyond these direct effects, the light from the first stars began establishing the ultraviolet background radiation that would persist and evolve throughout cosmic history. This ultraviolet background influenced chemical processes throughout intergalactic space, affecting the temperature, ionization state, and molecular composition of gas across the cosmos. The ionizing radiation also began heating the intergalactic medium on large scales through a process called photoheating. As photons ionized hydrogen atoms, they typically transferred excess energy to the freed electrons as kinetic energy. These energetic electrons then shared their energy through collisions, raising the overall temperature of the gas. This heating helped counteract gravitational collapse in certain regions, modulating the pace of structure formation. As more population 3 stars ended their brief lives in supernovae explosions, they added new influences to this evolving cosmic environment. Shock waves raced outward from these explosions, compressing gas in their paths and potentially triggering new episodes of star formation. The heavy elements they scattered, the first metals in cosmic history, began changing the cooling properties of gas in their vicinity. Gas enriched with even small amounts of carbon, oxygen, and other elements could cool more efficiently through fine structure line emission, a process where electrons in these atoms transition between energy levels, releasing photons that carry away energy. This enhanced cooling allowed enriched gas to collapse more readily into new stars, accelerating the cosmic star formation rate. The combined effects of ionization, heating, radiation pressure, chemical enrichment, and supernova shockwaves began reshaping the cosmic landscape. Regions that had been relatively uniform began developing complex structures, dense knots, where new stars would form, surrounded by heated, ionized cavities, where star formation was temporarily suppressed. This pattern of feedback and response created a self-regulating system. Too much star formation in a region would produce intense radiation and eventual supernovae that would suppress further star formation temporarily. Too little star formation meant insufficient feedback, allowing gravitational collapse to proceed more efficiently, increasing the star formation rate. Through these processes, the light from the first stars helped establish the foundations of cosmic self-regulation feedback cycles that continue to influence galaxy formation and evolution to the present day. Rather than proceeding at a uniform rate throughout the universe, star formation and structure development became clustered in space and episodic in time. The first light also began revealing the underlying density structure of the universe, illuminating the cosmic web that had been forming in the dark. In regions where slightly more matter had congregated due to initial quantum fluctuations amplified by gravity, more stars formed. Their light and energy further influenced these regions, enhancing the contrast between overdense and underdense zones. This growing contrast accelerated structure formation through gravitational attraction. Regions with more stars and more processed material attracted additional gas through gravity, growing even denser over time. Meanwhile, underdense regions remained relatively unaffected, evolving into the cosmic voids we observe in today's universe. As this process continued, the first stars and their light helped guide the transition from a relatively smooth universe to one characterized by distinct structures, the precursors to today's galaxies, galaxy clusters, and the cosmic web that connects them. The first light also created observable effects that astronomers can detect billions of years later. As these stars ionized the surrounding hydrogen, they set up conditions for hydrogen to absorb light at specific wavelengths when it later recombined in cooler environments. The pattern of this absorption creates what astronomers call the Lyman alpha forest, a series of absorption lines visible in the spectra of distant quasars. By studying this forest of absorption features, astronomers can map the distribution and state of hydrogen at different distances and times, tracing the evolution of cosmic structure. These observations help constrain when reionization occurred and how the first light transformed the universe. Another detectable consequence lies in the cosmic microwave background radiation, the afterglow of the Big Bang itself. As this ancient light traveled through the partially ionized universe, it scattered off free electrons, creating subtle polarization patterns. These patterns, detectable with sensitive microwave telescopes, provide additional constraints on when and how reionization unfolded. The James Webb Space Telescope, with its unprecedented infrared sensitivity, is designed specifically to observe the era when the first light transformed the universe. It may detect the collective glow from the first stars, or observe their supernovae, providing direct glimpses of cosmic dawn. Future radio observatories may detect the signature of neutral hydrogen absorption against the background of the first luminous objects, a pattern known as the 21-centimeter forest. This would provide complementary information about how the first light interacted with neutral regions between ionized bubbles. The significance of the first light extends beyond these technical considerations. It marks one of the most profound transitions in cosmic history, from a dark, relatively simple universe to one filled with light, complexity, and the beginnings of structure. It was the dawn of a new cosmic epoch, one whose consequences continue to shape our universe today. The light that emerged from the first stars began the process of cosmic enrichment and diversification that eventually led to our existence. Without this light and its effects on primordial gas, subsequent generations of stars would have formed differently. Galaxies might have developed along different evolutionary paths, and the conditions necessary for life might never have emerged. When we gaze at our star-filled sky today, we see the distant descendants of a process that began with those first luminous giants. The light that changed everything continues to shape cosmic evolution, now through the radiation from billions of galaxies across the observable universe. That first light represented more than just illumination, it was information, energy, and influence propagating across the cosmos. It carried the signature of nuclear fusion, the first complex atomic interactions, and the beginning of chemical diversity. It was the universe's first message, transmitted across space and time in the form of photons. Some of that ancient light is still traveling through the universe today, though now redshifted far beyond the visible spectrum. When our most sensitive telescopes detect this light, they're connecting us directly to those first moments when darkness gave way to dawn, when the universe first began to resemble the place we inhabit today. The study of how the first light transformed the universe connects multiple scientific disciplines: astrophysics, cosmology, nuclear physics, atomic physics, and computational science. It requires understanding processes that operate across vast scales of size and time, from subatomic particles to cosmic structures spanning millions of light years. As we continue to improve our observational capabilities and refine our theoretical models, we edge closer to a comprehensive understanding of this crucial transition. Each new discovery adds another piece to the puzzle, helping us reconstruct the story of how light first changed everything. The universe before the first stars was a place of simplicity and darkness. The universe after them was a place of growing complexity, chemistry, and illumination. That transition driven by the light from the first star set the stage for everything that followed, including, eventually, our own existence on a small planet orbiting an ordinary star. In a very real sense, we are children of that first light, descendants of a process set in motion when the first stars pierced the cosmic darkness and began transforming the universe around them. Their light changed everything, creating the conditions necessary for our cosmos to evolve from primordial simplicity to the rich complexity we observe today. How did the universe transition from isolated stars to the grand structures we call galaxies? In the aftermath of the first stellar explosions, a new chapter in cosmic evolution began, one that would transform individual beacons of light into the first collective stellar systems. The first stars did not form in galaxies as stars do today. They ignited as solitary giants, or in sparse groups, scattered through the primordial universe. But gravity, the patient architect of cosmic structure, was already working to bring these isolated stars together into the first protostructures that would eventually become galaxies. To understand how the first galaxies formed, we need to follow the complex interplay between gravity, light, and the expanding universe that unfolded during the first few 100 million years after the Big Bang. Remember that even before the first stars ignited, matter in the early universe wasn't perfectly uniform. Tiny quantum fluctuations, stretched to macroscopic scales during inflation, had created a subtle pattern of slightly denser and slightly less dense regions. Gravity amplified these initial differences, drawing more matter into already dense regions, while leaving less dense regions increasingly empty. This gravitational amplification created a cosmic web of filaments and no less vast network of matter stretching across the expanding universe. The densest regions, the nodes where filaments intersected, became the birthplaces of the first stars. But these same regions were destined to become something more, the seeds of the first galaxies. As the earliest population 3 stars formed in these dense nodes, they immediately began influencing their surroundings. Their intense ultraviolet radiation ionized nearby hydrogen, creating expanding bubbles of hot plasma. When they died in supernova explosions after just a few million years, they scattered newly forged heavy elements across space and sent powerful shock waves through surrounding gas. These processes had competing effects on subsequent star formation. The heating from radiation temporarily suppressed further collapse in already ionized regions. But the shock waves from supernovae could compress gas at their edges, potentially triggering new episodes of collapse. Meanwhile, the newly introduced heavy elements changed the cooling properties of the gas, allowing it to collapse more efficiently in regions enriched by previous stellar explosions. In the densest cosmic nodes, where material continued flowing in along intersecting filaments, these competing processes created cycles of star formation. New stars would form, live their brief lives, explode, and influence the formation of the next stellar generation. With each cycle, the region became more chemically enriched, and the pattern of stellar birth changed. While the first population 3 stars had formed in isolation or small groups, subsequent generations could form in more clustered patterns. The enhanced cooling from metals allowed gas clouds to fragment more efficiently, creating multiple stars from a single collapsing cloud. This shift toward clustered star formation represented a crucial step toward galaxy formation. Gravity continued working to bind these growing stellar clusters together. The combined mass of stars, gas, and the invisible dark matter that had been concentrated in these regions created gravitational wells that attracted even more material from their surroundings. The regions grew not just through star formation, but through the continued infall of gas along cosmic filaments. Computer simulations show that the first substantial stellar groupings, what we might call proto-galaxies, likely formed between 200 and 500 million years after the Big Bang. These were not yet the majestic spiral or elliptical galaxies we see today. They were irregular, chaotic collections of stars embedded in clouds of gas, perhaps comparable in size to the small Magellanic Cloud, a satellite galaxy of our Milky Way that contains about 3 billion stars. These proto-galaxies continued growing through 2 main processes: the birth of new stars from inflowing gas and mergers with other proto-galaxies. When 2 such systems collided, their stars typically passed by each other without direct collision. Space is mostly empty, even in these dense regions. But their gas clouds could collide, compress, and trigger intense bursts of new star formation. Their dark matter halos merged, creating deeper gravitational wells that could attract even more material. The earliest proto-galaxies were likely dominated by what astronomers call population 2 stars, the second generation of stars in cosmic history. These stars formed from gas that had been lightly enriched with metals from the first supernovae. While still metal poor compared to stars born today, they contained enough heavy elements to change their properties significantly. Population 2 stars could form with a range of masses, unlike the predominantly massive population 3 stars. Some were giants that lived short lives like their predecessors, while others were small enough to burn slowly and survive for billions of years. Some of these ancient low-mass stars still exist today in the halos of modern galaxies, providing astronomers with direct fossil evidence of this early period of cosmic history. The makeup of the first proto-galaxies likely varied significantly depending on their formation history. Those that formed in regions where many population 3 stars had previously lived and died would have higher metal content and different stellar populations than those forming in more pristine regions. This diversity established patterns of chemical evolution that would continue through cosmic history. The James Webb Space Telescope has started to reveal these ancient proto-galaxies to our modern eyes. By observing infrared light that has traveled for more than 13 billion years, it captures images of proto-galaxies as they appeared when the universe was just a few 100 million years old. These observations confirm theoretical predictions about their small sizes, irregular shapes, and intense star formation activity. Another crucial factor in proto-galaxy formation was dark matter, the invisible substance that outweighs ordinary matter by about 5 to 1 in our universe. While dark matter doesn't interact through electromagnetic forces, meaning it doesn't absorb, emit, or reflect light, it does exert gravity. In fact, dark matter provided the primary gravitational scaffolding around which the first galaxies formed. Computer simulations show that dark matter began clustering earlier than ordinary matter, forming halos of various sizes. The most massive of these dark matter halos attracted large amounts of gas, which could then cool and collapse to form stars. The relationship between dark matter halos and the galaxies they hosted established patterns that continue to the present day. More massive halos generally host more massive galaxies. As proto-galaxies grew larger and formed more stars, they began generating substantial amounts of energy that pushed back against the very processes forming them. This feedback took several forms: radiation pressure from stars, stellar winds that expelled gas, and most dramatically, supernovae explosions that could heat and eject significant amounts of gas. In smaller protogalaxies, this feedback could be powerful enough to expel much of the remaining gas, temporarily halting star formation until more gas could be accreted from surrounding space. This processed the cycle of inflow, star formation, feedback, and renewed inflow helped regulate the growth of these early systems and establish patterns of episodic star formation that would characterize many galaxies throughout cosmic history. Larger protogalaxies, with their deeper gravitational wells, could better retain their gas against these feedback processes. This allowed them to form stars more continuously and grow more quickly, establishing a relationship between galaxy mass and star formation efficiency that would persist through time. The formation of the first substantial protogalaxies also marked a crucial phase in the reionization of the universe. While individual population 3 stars had begun the process of ionizing the neutral hydrogen that filled space, the collective ultraviolet radiation from star-forming protogalaxies accelerated it dramatically. By about 1 billion years after the Big Bang, most hydrogen in intergalactic space had been reionized, fundamentally changing the environment in which subsequent galaxy formation would occur. As protogalaxies continued to merge and grow, they began developing more organized structures. Gas settling into these systems often formed rotating disks due to conservation of angular momentum, the same principle that causes figure skaters to spin faster when they pull in their arms. Stars formed within these rotating gas disks inherited their motion, creating the first disk galaxies in cosmic history. Other protogalaxies experienced more chaotic mergers that scrambled the orbits of their stars, creating spheroidal systems without organized rotation. These became the precursors to today's elliptical galaxies. The balance between orderly growth through gas accretion and chaotic growth through mergers helped determine the morphological fate of each system. By about 1 billion years after the Big Bang, many of the essential features of the galaxy population were established. There were massive galaxies and dwarf galaxies. There were systems dominated by ordered rotation and systems with more random stellar motions. There were galaxies actively forming stars and galaxies where star formation had been temporarily suppressed by feedback or gas depletion. The universe had transitioned from isolated stars to a complex ecosystem of interacting galaxies, setting the stage for billions of years of continued evolution that would eventually produce the rich variety of galaxies we observe today. The formation of protogalaxies also marked a crucial transition in how stars themselves formed. In the era of the first stars, stellar birth was a relatively simple process driven by the collapse of pristine hydrogen clouds. But within protogalaxies, star formation became an increasingly complex, self-regulating process influenced by previous generations of stars, enriched gas chemistry, magnetic fields, turbulence, and radiation feedback. As protogalaxies evolved, they began developing the internal structures that would characterize mature galaxies. Gas clouds within them became the sites of clustered star formation, creating stellar nurseries similar to those we observe in nearby galaxies today. Some regions of intense star formation grew large enough to be visible across cosmic distances as bright blue knots within their host protogalaxies. The heaviest stars in these systems continued to forge elements heavier than iron through processes like the rapid neutron capture process, R process, during their explosive deaths. This further enriched the interstellar medium within protogalaxies, enabling the formation of planetary systems more similar to our own solar system in subsequent stellar generations. The most massive protogalaxies likely began developing another feature that would become central to galaxy evolution: supermassive black holes. While the first stars had left behind stellar mass black holes with tens or hundreds of solar masses, the centers of growing protogalaxies created environments where these seed black holes could merge and accrete material rapidly. Through processes still not fully understood, some of these black holes grew at remarkable rates, reaching millions of solar masses within just a few 100 million years. As they accreted surrounding gas, they generated tremendous energy, producing some of the most luminous objects in the universe, the first quasars. These quasars, powered by supermassive black holes in the centers of massive protogalaxies, became beacons visible across cosmic distances. They poured energy into their surroundings, potentially influencing the evolution of their host galaxies through feedback processes even more powerful than those generated by stars. The relationship between protogalaxy formation and chemical enrichment had profound implications for the long-term evolution of the universe. With each generation of stars, the interstellar medium became increasingly enriched with heavier elements. This changing chemical composition affected everything from how gas cooled and collapsed to form stars to the nature of the planetary systems those stars could produce. In regions where multiple generations of stars had lived and died, the interstellar medium contained enough carbon, oxygen, silicon, and iron to eventually form rocky planets like Earth. The building blocks of life-complex organic molecules could begin to form in these chemically enriched environments. The transition from pristine gas to chemically complex systems was well underway. The formation of protogalaxies also established patterns of environmental influence that would persist throughout cosmic history. Protogalaxies didn't evolve in isolation, they influenced each other through gravitational interactions, mergers, and the radiation they emitted. Protogalaxies forming in dense regions with many neighbors evolved differently from those forming in more isolated environments. By studying the oldest galaxies visible with our most powerful telescopes, astronomers can trace how these patterns of environmental influence developed over time. They can identify protoclusters, dense regions containing multiple protogalaxies that would eventually merge to form the massive galaxy clusters we see today. These observations confirm that the basic hierarchy of cosmic structure, from stars to galaxy groups, to galaxy clusters, was established in the first billion years after the Big Bang. The seeds planted during protogalaxy formation would grow into the rich cosmic ecosystem we observe in the present-day universe. Perhaps most remarkably, the formation of protogalaxies created the environments in which subsequent cosmic evolution would unfold. Stars born within protogalaxies interacted with each other and with interstellar gas in ways that isolated stars could not. These interactions spurred new patterns of evolution, enabling the development of more complex stellar systems, including those with planets. The transition from isolated stars to the first galaxies represents one of the most significant phases in cosmic history, the emergence of collectivity. Individual stars combined into systems with new properties and capabilities beyond the sum of their parts. Cycles of stellar birth, life, and death became self-sustaining within these protogalaxies, establishing patterns that would continue for billions of years. When we look at ancient protogalaxies with our most powerful telescopes, we're witnessing the universe's first steps toward the complex, hierarchical structure that characterizes our cosmos today. We're seeing the embryonic forms of systems that would eventually evolve into majestic spiral galaxies, like our Milky Way, or massive elliptical galaxies at the centers of galaxy clusters. These first collective stellar systems were the crucibles in which cosmic evolution accelerated. They created environments where chemistry could grow more complex, where stellar systems could develop in new ways, and where the foundations for eventual biological complexity could be established. The story of protogalaxy formation connects directly to our own origins. Our Sun formed within the Milky Way about 4.6 billion years ago, but the Milky Way itself began as a collection of protogalaxies that merged over cosmic time. The atoms in our bodies were forged in stars that lived and died within these ancestral systems. When we study protogalaxy formation, we study an essential chapter in our own cosmic lineage. As we continue developing more powerful observational tools and more sophisticated computer simulations, our understanding of this crucial transition continues to deepen. The James Webb Space Telescope is currently revolutionizing our view of the earliest galaxies, revealing systems that formed when the universe was just a few 100 million years old. Future facilities like the Extremely Large Telescope and the Square Kilometre Array will push these observations even further. The formation of protogalaxies marks the beginning of cosmic adolescence, the transition from the simplicity of the early universe to the rich complexity of the developed cosmos. It was when the universe first began to resemble the place we recognize today, with stars gathered into collective systems that would eventually create the conditions necessary for planets and life. In these ancient stellar nurseries, the universe took its first steps toward the magnificent cosmic ecosystem we inhabit today. The lone stars of cosmic dawn gave way to the first galactic communities, and the universe would never be the same again. How do astronomers search for objects that vanished billions of years before Earth even formed? The quest to find evidence of population 3 stars represents one of modern astronomy's greatest challenges and, potentially, one of its most rewarding pursuits. The first stars are believed to have lived and died over 13 billion years ago. Their light has been traveling through space ever since, stretched by the expanding universe to wavelengths far beyond what human eyes can see. To detect these ancient signals requires extraordinary instruments, innovative techniques, and remarkable persistence. The fundamental challenge is straightforward but daunting. Population 3 stars no longer exist in our universe. These massive, brilliant objects burned through their nuclear fuel in just a few million years. Cosmic eye blink. All of them died long before our solar system formed. We cannot observe them directly as we can observe stars in our galaxy. Instead, astronomers search for several types of evidence that could reveal the presence and properties of these elusive first luminaries. First, and most promising, is the possibility of detecting supernova explosions from population 3 stars. When these massive stars died, many exploded as extraordinarily energetic supernovae. The light from these explosions would have been intense enough to potentially remain visible across cosmic distances. A particularly powerful type of explosion, associated with very massive population 3 stars, is the pair instability supernova. These cataclysmic events occur when the cores of stars between roughly 140 and 260 solar masses become so hot that energy spontaneously converts into electron-positron pairs. This sudden energy conversion reduces pressure support, causing the star to partially collapse, triggering runaway fusion that completely disrupts the star. These explosions could be up to 100 times more energetic than typical supernovae we observe today. Their unique spectral signatures, particularly their unusual chemical abundance patterns, with large amounts of elements like nickel, might be detectable with sensitive infrared telescopes, like the James Webb Space Telescope, JWST. Launched in December 2021, JWST represents humanity's most powerful tool for searching for signs of the first stars. Its sensitive infrared instruments can detect extremely faint signals from the early universe. By observing deep fields areas of sky selected for long-duration observations, astronomers hope to capture the flash of a population 3 supernova among the thousands of distant galaxies visible. Even if we can't catch a population 3 star in the act of exploding, we might detect the after-effects of these explosions in the form of ancient supernovae remnants. As the ejected material from these explosions expanded into surrounding gas, it would have created distinctive structures potentially observable with future radio telescopes. Another promising approach involves searching for the chemical signatures of population 3 stars in their stellar descendants. When the first stars exploded, they scattered their newly forged elements across space. Some of this enriched material was incorporated into the next generation of stars, population 2 stars. Some of these second-generation stars, if they were small enough, could still exist today. Astronomers search our galaxy's halo for extremely metal-poor stars that might preserve chemical patterns unique to population 3 nucleosynthesis. These ancient stellar fossils carry the elemental fingerprints of the first stars that lived and died before them. By meticulously analyzing their spectra, breaking their light into its component wavelengths, researchers can identify unusual abundance patterns that point to specific types of population 3 progenitors. Several candidates for these second-generation stars have been discovered, with colorful names like Heone 107 5000, 240, and SMSSJ 313 6708. These stars have iron abundances less than 1/10,000th that of our Sun, suggesting they formed from gas polluted by just one or a few population 3 supernovae. What makes this approach particularly valuable is that different types of population 3 stars would have produced different elemental signatures. A 200 solar mass star exploding as a pair instability supernova would create a different mix of elements than an 80 solar mass star exploding as a core collapse supernova. By identifying these patterns in surviving ancient stars, astronomers can reconstruct aspects of the first stellar population. A third approach involves looking for the collective light from the first stars. While individual population 3 stars are too faint and distant to detect directly, their combined light might create a detectable background signal. This cosmic infrared background contains the accumulated light from all sources too faint to resolve individually. By carefully measuring this background and subtracting known contributions from galaxies and other sources, astronomers hope to isolate the component coming from the first stars. This approach requires extremely precise measurements and sophisticated statistical techniques to separate the different contributions to the observed background. Complementing these observational approaches, radio telescopes offer another window into the era of the first stars. As ultraviolet light from these stars began ionizing the neutral hydrogen that filled the early universe, it created patterns of ionized and neutral regions. These patterns affected how the hydrogen absorbed and emitted radio waves at a characteristic wavelength of 21 centimeters. By mapping this 21 centimeter signal across different distances and thus different times in cosmic history, radio astronomers hope to trace the emergence and impact of the first stars. Several major radio telescope arrays, including the Hydrogen Epoch of Reionization Array, HERA, and the Future Square Kilometer Array, SKA, are designed specifically to detect this signal. The challenge is immense. The 21 centimeter signal from the early universe is extremely faint and buried under foreground emissions that are thousands of times stronger. Detecting it requires not only sensitive instruments, but also sophisticated data processing techniques to remove these foregrounds without erasing the delicate cosmic signal. Computer simulations also play a crucial role in the search for population 3 stars. By modeling the physics of the early universe from the collapse of primordial gas clouds to the nuclear reactions inside the first stars to their explosive deaths, researchers can predict what observational signatures to look for. These simulations have grown increasingly sophisticated, incorporating complex physics like magnetohydrodynamics, radiative transfer, and nuclear reaction networks. They allow astronomers to test hypotheses about the first stars and plan observational strategies to detect their signatures. One particularly promising frontier combines all these approaches through the study of the very earliest galaxies. While individual population 3 stars may be beyond our observational reach, the proto-galaxies that formed around them might be detectable with our most powerful telescopes. The James Webb Space Telescope has already identified galaxy candidates from when the universe was less than 400 million years old. These early systems might still contain some actively shining population 3 stars or their immediate descendants. They might also preserve distinctive signatures in their spectra that reveal the influence of the first stellar generation. For example, the presence of strong helium emission lines, combined with an absence of metal lines, could indicate a galaxy dominated by population 3 stars. Alternatively, unusual abundance patterns in a galaxy's interstellar medium might reveal the chemical legacy of the first supernovae. As observational capabilities continue advancing, astronomers are exploring increasingly creative approaches to finding evidence of the first stars. Some researchers are searching for gravitational lensing events, where a massive foreground object magnifies light from distant sources that might temporarily boost the signal from early stellar populations to detectable levels. Others are investigating whether gamma-ray bursts, brief but incredibly powerful flashes of high-energy radiation from the deaths of rapidly rotating population 3 stars might be detectable with current or future satellites. These primordial gamma-ray bursts would have distinctive properties that could distinguish them from more recent explosions. The field is also exploring whether neutrinos, nearly massless subatomic particles that rarely interact with matter from population 3 supernovae, might be detectable. While most neutrinos from these ancient explosions would have passed through Earth long ago, the diffuse supernova neutrino background includes contributions from all supernovae throughout cosmic history, including the first generation. Despite these diverse approaches, the search for population 3 stars remains one of astronomy's greatest challenges. The signals are incredibly faint, buried under foregrounds thousands of times stronger, and potentially confusable with other cosmic sources. The timescales involved looking back more than 13 billion years push our observational capabilities to their limits. Yet the scientific payoff would be extraordinary. Direct evidence of the first stars would test our understanding of early cosmic evolution, primordial chemistry, and the physics of star formation under exotic conditions. It would connect theoretical models to observable reality and potentially resolve debates about the characteristics of these pioneering stellar giants. Moreover, the first stars represent a unique population that can never be repeated. They formed under conditions, the absence of metals, the pristine state of the early universe that no longer exist anywhere in our cosmos. They are a singular chapter in cosmic history, one that shaped everything that followed. The search also connects to fundamental questions about our own origins. The first stars forged the initial batches of carbon, oxygen, and other elements essential for planets and life. They helped shape the environments where subsequent stellar generations would form. They were the universe's first alchemists, transforming the simple chemistry of the early cosmos into the complex elements necessary for our existence. As observational technology continues advancing, our chances of detecting these ancient luminaries improve. The James Webb Space Telescope represents just the beginning of a new era in the exploration of cosmic dawn. Future facilities like the Extremely Large Telescope, with its 39-meter primary mirror, will push our observational horizon even further back in time and detect even fainter signals. But perhaps the most exciting prospects lie in unexplored wavelengths. The low-frequency radio regime, accessible through facilities like the Square Kilometre Array, offers a unique window into the era of the first stars through the 21-centimeter hydrogen signal. This global signal, combined with its spatial fluctuations, could reveal when the first stars ignited, how they were distributed, and how they affected their surroundings. Computer simulations will continue growing in sophistication, helping interpret these observations and refine our theoretical understanding. The combination of advanced observations, powerful simulations, and innovative analytical techniques promises to gradually lift the veil on this elusive chapter in cosmic history. For now, the search continues a testament to human curiosity and perseverance in the face of extraordinary challenges. With each new observation, each refined simulation, and each creative analytical approach, we edge closer to glimpsing the stars that first illuminated our universe, the pioneers that transformed darkness into light and simplicity into complexity. How does one build a time machine to see the universe's first light? For astronomers searching for the earliest stars and galaxies, the James Webb Space Telescope, JWST, represents humanity's most advanced tool for peering back to cosmic dawn. Launched on December 25, 2021, after decades of development, this extraordinary observatory is specifically designed to explore the universe's infancy, including the era when the first stars shone. Unlike conventional time machines of science fiction, JWST doesn't physically transport us to the past. Instead, it captures ancient light that has been traveling through space for billions of years. This light carries information about objects as they appeared in the distant past, a natural cosmic time capsule that allows us to witness earlier chapters in the universe's history. What makes JWST particularly suited for this task? The key lies in its ability to observe infrared light. As the universe expands, light waves from distant objects are stretched, a phenomenon astronomers call redshift. Light that was originally emitted as ultraviolet or visible light from the first stars and galaxies has been stretched into infrared wavelengths during its multi-billion-year journey to Earth. To capture this ancient infrared light, JWST features a primary mirror, 6.5 meters, 21.3 feet, in diameter, composed of 18 hexagonal gold-plated beryllium segments. This massive mirror, over 6 times the collecting area of its predecessor, the Hubble Space Telescope, gathers the feeble infrared photons that have traveled across cosmic time. But collecting this light is only part of the challenge. To detect the faint infrared signals, JWST must be extraordinarily cold. Infrared light is essentially heat radiation, so any warm object, including the telescope itself, would emit infrared light that would overwhelm the distant signals astronomers seek. To prevent this, JWST operates at temperatures below 370 degrees Fahrenheit, 223 degrees Celsius, by deploying a tennis court-sized sun shield that blocks heat and light from the Sun, Earth, and Moon. The telescope orbits approximately 1.5 million kilometers, 930 miles, from Earth at the second Lagrange point, Lane 2, where the gravitational forces of the Sun and Earth balance to create a stable location. This distant orbit keeps the telescope away from Earth's heat and provides an unobstructed view of the universe. Armed with these capabilities, JWST is transforming our understanding of the early universe through several key observation strategies designed to detect evidence of the first stars. The first approach involves making ultra-deep observations of small patches of sky, similar to the famous Hubble Deep Field images, but pushing much further into the universe's infancy. By pointing at seemingly empty regions of space for hundreds of hours, JWST can accumulate enough light to reveal extraordinarily distant and faint objects, including galaxies that formed just a few 100 million years after the Big Bang. These observations have already yielded surprises. Within months of beginning scientific operations, JWST detected galaxy candidates from when the universe was less than 400 million years old, earlier than many theoretical models had predicted galaxies could form. Some of these early systems appear unexpectedly bright and mature, challenging existing theories about how quickly the first substantial cosmic structures assembled. While these observations haven't yet directly detected population 3 stars, they're approaching the epoch when these first stars should have existed. As JWST continues its mission and accumulates more deep observations, it may push the observational frontier back to the time of the first stellar generation. A second approach involves searching for distinctive spectral signatures that would reveal the presence or influence of population 3 stars. JWST's sensitive spectrographs can break light from distant sources into its component wavelengths, revealing information about their composition and physical conditions. Population 3 stars were composed almost entirely of hydrogen and helium, unlike later stellar generations that contain heavier elements. This unique composition would create distinctive spectral patterns. A galaxy containing active population 3 stars would show strong hydrogen and helium emission lines, but lack the metal lines characteristic of more chemically enriched systems. Alternatively, JWST might detect the chemical signatures of the first stars in the aftermath of their explosive deaths. Certain types of population 3 supernovae, particularly pair instability, supernovae from very massive stars would have produced unique abundance patterns distinguishable from later stellar explosions. Finding these patterns in ancient galaxies would provide strong indirect evidence for the nature of the first stars. A third strategy involves searching for individual supernovae from population 3 stars. While the stars themselves may be too faint to detect directly across such vast distances, their explosive deaths could produce brief but intense flashes, potentially visible even from the cosmic dawn era. This approach requires not just deep observations but patient monitoring of the same fields over time to catch these rare, brief events. When a supernova occurs, astronomers can quickly perform follow-up spectroscopic observations to determine whether its characteristics match those expected from population 3 explosions. JWST is also investigating the process of cosmic reionization, the period when light from the first luminous objects transformed the neutral hydrogen that filled the universe back into an ionized plasma. By studying galaxies from different epochs during this transition, astronomers can track how the process unfolded and determine the relative contributions of stars, protogalaxies, and possibly other sources like accreting black holes. The telescope's ability to detect faint infrared signals also allows it to potentially measure the cosmic infrared background, the accumulated light from all sources too distant or faint to resolve individually. Within this background may lurk the collective glow from the first generation of stars, distinguishable through its unique spectral characteristics. Beyond these direct approaches, JWST is revolutionizing our understanding of the environments in which the first stars formed. By mapping the distribution and properties of early galaxies, it reveals how cosmic structure emerged from the relatively smooth early universe. This environmental context is crucial for understanding when, where, and how the first stars ignited. The telescope is also providing unprecedented views of star formation in more recent epochs. By studying this process in different environments and at different times, astronomers can develop better models of how stars form under various conditions models that can then be extrapolated back to the more exotic conditions of the early universe. The first 2 years of JWST observations have already challenged some established theories about the early universe. The detection of surprisingly massive and mature galaxies within the first 500 million years after the Big Bang suggests that cosmic structure may have developed more quickly than previously thought. This in turn raises questions about when and how the first stars formed. Some researchers suggest these observations might indicate that the first stars formed earlier than current models predict, perhaps as early as 100 million years after the Big Bang rather than the typically estimated 180 million years. Others propose that early star formation might have been more efficient than expected, allowing more stars to form quickly from the available primordial gas. Another possibility is that the first stellar generations included more low-mass stars than current theories suggest. While the literature tends to focus on massive population 3 stars with 40 to 300 solar masses, some models leave room for lower mass examples. If a significant population of low-mass population 3 stars formed, some might still exist today, offering the tantalizing possibility of directly observing first-generation stars that have survived for over 13 billion years. JWST observations have also revealed unexpected patterns in the chemical composition of the earliest observable galaxies. The detection of elements like oxygen in systems just 400 million years after the Big Bang indicates that star formation and chemical enrichment proceeded rapidly in some regions. These findings help constrain the timeline of when the first stars lived, died, and enriched their surroundings. The telescope's exquisite sensitivity allows astronomers to measure not just the presence of various elements, but their relative abundances. These abundance patterns serve as chemical fingerprints that can distinguish between enrichment from different types of stellar explosions. As more data accumulates, these measurements may reveal the unique chemical signatures of population 3 supernovae. Beyond specific observations, JWST is advancing our understanding of the first stars by enabling comprehensive surveys of the early universe. By systematically cataloging thousands of ancient galaxies across different areas of the sky, astronomers can develop statistical measures of when and how rapidly cosmic structure emerged. These surveys also identify the most promising candidates for follow-up observations seeking direct evidence of population 3 stars. Perhaps most excitingly, JWST offers the possibility of unexpected discoveries that could revolutionize our understanding of cosmic dawn. The history of astronomy is filled with instances where new observational capabilities revealed phenomena never anticipated in theoretical models. As JWST peers deeper into cosmic history than ever before possible, it may similarly uncover aspects of the early universe that current theories haven't predicted. For example, some researchers speculate that under certain conditions, the first stars might have formed not as individuals or small groups, but as densely packed clusters. If such clusters existed, their collective light might be detectable with JWST, even if individual stars remain below the detection threshold. Others suggest that interactions between the first stars and dark matter, the mysterious substance that outweighs ordinary matter by about 5-to-1, might have produced observable effects. If dark matter consists of particles that can annihilate when they meet, this process might have been enhanced in regions where the first stars formed, potentially producing distinctive radiation signatures. As observations continue accumulating, astronomers are developing increasingly sophisticated techniques to extract information about the first stars from JWST data. Machine learning algorithms now help identify the most promising distant galaxy candidates from among thousands of sources in deep field images. Statistical methods can detect patterns too subtle for human analysis, potentially revealing the collective influence of population 3 stars, even when individual objects remain unresolved. The quest to find the first stars with JWST exemplifies modern astronomy's interdisciplinary nature. It combines observational astronomy, theoretical astrophysics, cosmology, nuclear physics, computational science, and data analytics. Success requires not just the remarkable technological achievement of the telescope itself, but also the collaborative effort of researchers across multiple fields. While JWST represents our most powerful tool for exploring cosmic dawn, it's also part of a broader observational strategy. Its infrared observations complement those from radio telescopes like the upcoming Square Kilometre Array, which will map the distribution of neutral hydrogen during the era of the first stars. Together, These facilities will observe the early universe across different wavelengths, providing complementary perspectives on this critical period. As JWST continues, its mission expected to last at least 20 years, it will systematically push our observational horizon back toward the time of the first stars. With each new deep field, each spectroscopic measurement of an ancient galaxy, and each detection of a distant supernova, we edge closer to glimpsing the universe's first light. The telescope's name honors James E. Webb, who led NASA during the crucial early years of the Apollo program. Like the moon landings that Webb helped make possible, JWST represents a triumph of human curiosity, ingenuity, and perseverance. It allows us to explore not across physical space, but across time back to the universe's infancy, when the first stars transformed darkness into light. In this quest to observe the unobservable, to detect objects that vanished billions of years before Earth formed, JWST embodies humanity's enduring desire to understand our origins. The first stars were crucial links in the chain of cosmic evolution that eventually led to our existence. By studying them, we study our own most distant ancestry, the beginning of the stellar lineage that would eventually create the elements of life and the conditions for our emergence. Can ancient stars still visible today tell us about the universe's first generation? While population 3 stars themselves have long since disappeared, their influence persists in the chemistry and structure of stars. We can observe stellar fossils that preserve evidence of the cosmic dawn. To understand this connection between modern stars and their ancient predecessors, we need to explore how stellar generations relate to each other through a concept astronomers call galactic archaeology. Much as traditional archaeologists excavate layers of human history from the ground, galactic archaeologists study successive generations of stars to reconstruct the timeline of cosmic chemical evolution. Each stellar generation inherits material from previous generations and passes enriched material to the next, creating a continuous lineage that connects today's stars to the very first luminaries. The most direct links to population 3 stars are found in a rare category of ancient, low-mass stars called extremely metal, poor, EMP, stars. These extraordinary objects contain less than 1/10th the abundance of elements heavier than helium compared to our Sun. Some contain less than 1/1,000,000th the solar abundance of iron. These stellar fossils likely formed very early in cosmic history, from gas that had been enriched by just one or a few population 3 supernovae. Their chemical compositions represent something like a direct snapshot of the elements created in the first stellar explosions, preserved for nearly 13 billion years in these low-mass, slowly evolving stars. One famous example is a star with the technical designation SMSS J31000, 300.3, 670,839.3, located in the halo of our Milky Way galaxy. This ancient star shows no detectable iron in its spectrum, but contains small amounts of carbon. This unusual pattern suggests it formed from gas polluted by a single population 3 star that exploded as a relatively low-energy supernova 1 that created carbon but failed to produce significant quantities of iron. Another remarkable fossil is H1000, 327-2000, 326, one of the most metal-poor stars known. Its unusual abundance, pattern-high levels of carbon, nitrogen, and oxygen relative to iron provides clues about the specific types of population 3 stars that enriched the gas from which it formed. By carefully modeling various first-generation supernovae, astronomers can determine which scenarios best explain the observed chemical fingerprint. These stellar fossils are rare treasures in our cosmic neighborhood. Finding them requires extensive survey work, as perhaps only 1 in a million stars in our galaxy has the extreme metal-poor characteristics that identify it as a second-generation star. But each discovery provides another piece in the puzzle of understanding population 3 stars. What makes these ancient survivors such valuable time capsules is that low-mass stars evolve extremely slowly. A star with 80% of our Sun's mass can shine steadily for more than 20 billion years longer than the current age of the universe. This means that low-mass stars formed in the early universe are still with us today, largely unchanged in their core composition. By meticulously analyzing the spectra of these stars, breaking their light into its component wavelengths, astronomers can determine not just the presence of various elements, but their precise abundances relative to each other. These abundance patterns serve as chemical fingerprints that can distinguish between enrichment from different types of stellar explosions. For example, a regular core collapse supernova from a 25 solar mass population 3 star would produce a different mix of elements than a pair instability supernova from a 200 solar mass giant. These distinct patterns, preserved in second-generation stars, allow astronomers to reconstruct aspects of the first stellar population, their typical masses, explosion energies, and nucleosynthesis processes. Some particularly intriguing evidence comes from the abundances of elements created through the rapid neutron capture process, or R process. Elements like europium and gold are primarily forged in extreme environments where atomic nuclei rapidly capture neutrons before they can decay. The exact sites of R process nucleosynthesis remain debated, but candidates include neutron star mergers and certain types of supernovae. The presence of R process elements in some extremely metal-poor stars indicates that these processes were already occurring very early in cosmic history. This provides clues about not just the first stars but also their remnants and how they interacted in the early universe. Beyond individual stellar fossils, astronomers also study the overall distribution of chemical compositions in different parts of our galaxy. The Milky Way's halo, a spherical region surrounding the familiar disk, contains many of the oldest stars in our galaxy. By mapping chemical patterns across the halo, researchers can reconstruct the early chemical evolution of our galactic neighborhood. These studies reveal that chemical enrichment in the early universe was not uniform. Some regions were polluted by multiple supernovae, creating complex abundance patterns, while others preserved the signatures of individual explosions. This patchiness persisted until enough mixing had occurred to homogenize the interstellar medium, a process that took hundreds of millions of years. The legacy of population 3 stars extends beyond these direct chemical fossils. Their influence shaped the evolution of entire stellar populations that followed them. By changing the chemical composition of the interstellar medium, they altered how gas cooled and collapsed to form new stars, affecting everything from the typical masses of subsequent stellar generations to the efficiency of star formation processes. This shift is visible in what astronomers call the initial mass function, IMF, the distribution of masses with which stars form. Theory suggests that population 3 stars had a top-heavy IMF, forming predominantly high-mass stars due to inefficient cooling in metal-free gas. As metals were introduced into the interstellar medium by the first supernovae, cooling became more efficient, allowing lower-mass stars to form more readily. The transition from the top-heavy IMF of population 3 to the more balanced IMF we observe today represents a fundamental change in how the universe forms, stars, a change initiated by the first stellar generation. This transition is reflected in the mix of stellar masses observed in different environments and at different epochs in cosmic history. Population 3 stars also helped establish the pattern of element production that has continued throughout cosmic history. The fusion processes that power stars and create new elements follow the same physical laws today as they did 13 billion years ago. But the starting compositions, masses, and environments of stars have changed dramatically. By comparing theoretical models of nucleosynthesis in population 3 stars with the observed abundances in early second-generation stars, astronomers can test and refine their understanding of stellar nucleosynthesis more generally. These ancient abundance patterns provide crucial constraints on models of how elements form inside stars of all generations. Another fascinating legacy lies in the remnants that population 3 stars left behind. When massive stars die, they can leave behind neutron stars, or black holes. These compact objects from the first stellar generation may still exist today, though identifying them presents extreme challenges. Some researchers have suggested that primordial black holes, those formed directly from the first stars, might be distinguished from later generations by their masses, spins, or locations within galaxies. While no confirmed population 3 remnant has been identified, the search continues using gravitational wave detectors that can detect mergers between black holes across cosmic distances. The influence of population 3 stars even extends to modern stellar evolution. When we observe massive stars today, like those in the Roan 136 cluster in the Large Magellanic Cloud, we're seeing objects that follow evolutionary pathways established billions of years ago. The physical processes operating in these modern giants connect directly to those that powered the first luminous objects in our universe. Studying this connection requires sophisticated computer simulations that model stellar evolution across different metallicities. These models reveal how the same fundamental physics, nuclear fusion, radiative transfer, convection, mass loss produces different outcomes depending on a star's chemical composition. By extrapolating to zero metallicity, researchers can predict the properties and behaviors of the unobservable first stars. Perhaps most profoundly, the legacy of Population 3 stars includes our own Sun and its planetary system. The elements that make up Earth, iron in its core, silicon in its mantle, carbon in its biosphere, were forged through countless generations of stellar nucleosynthesis, beginning with the first stars. By the time our solar system formed about 4.6 billion years ago, the interstellar medium had been enriched by roughly 10 billion years of stellar activity. The material that formed the Sun and planets included contributions from thousands of previous stellar generations, each adding to the chemical diversity that would eventually enable life on Earth. In this sense, we are all children of the stars, not just poetically, but literally. The atoms in our bodies were created inside stars through nuclear fusion and scattered across space when those stars died. The first step in this grand cycle of cosmic enrichment was taken by Population 3 stars, the universe's first alchemists. As observational capabilities continue advancing, we edge closer to more complete understanding of these connections. Massive spectroscopic surveys like SIGU, Sloan Extension for Galactic Understanding and Exploration, APOGEE, Apache Point Observatory Galactic Evolution Experiment, and the upcoming foremost 4-meter multi-object spectroscopic telescope are systematically mapping the chemical compositions of millions of stars across our galaxy. These surveys are revealing the full diversity of stellar chemistry in unprecedented detail, allowing researchers to identify previously unknown populations of ancient stars. They're also enabling statistical analyses that can detect subtle patterns in chemical evolution that might otherwise remain hidden. Next-generation facilities like the Extremely Large Telescope, with its 39-meter primary mirror, will push these observations further, potentially detecting even fainter ancient stars and measuring their compositions with greater precision. This continuous improvement in observational capabilities promises to strengthen the connections between today's visible stars and their long-vanished ancestors. The legacy of the first stars surrounds USIN, the chemistry of stars we observe today, in the structure of our galaxy and in our own bodies. By studying this legacy, we connect to the earliest chapters of stellar evolution and to the origins of the elements essential for life. Though Population 3 stars themselves have long since disappeared, their influence echoes through cosmic history, written in the stars that still shine in our night sky. How did points of light, scattered across the dark early universe, influence the grand cosmic structures we see today? The first stars did more than just illuminate the darkness, they helped sculpt the very architecture of our universe, establishing patterns that would persist for billions of years. To understand this profound influence, we need to explore how radiation, explosive energy, and chemical enrichment from the first stars shaped the distribution and properties of matter across cosmic scales. When the first stars ignited, they immediately began transforming their surroundings through radiation. Their intense ultraviolet output ionized nearby hydrogen, creating expanding bubbles of hot plasma. As these ionized regions grew and merged, they fundamentally altered the physical state of matter across the universe. This process, cosmic reionization, changed how gravity could act on gas. Neutral hydrogen can cool efficiently and collapse under gravity, but ionized hydrogen remains hot and resists compression. By ionizing the gas in some regions while leaving other areas neutral, the first stars created a patchwork of environments with different susceptibilities to gravitational collapse. In regions that had been ionized, further gas collapse and star formation were temporarily suppressed. The hot plasma resisted compression, requiring more time to cool and more gravitational force to overcome its pressure. Meanwhile, at the boundaries between ionized and neutral regions, compression from expanding ionization fronts could actually trigger new collapse and star formation. This pattern of alternating suppression and enhancement created a self-regulating system that influenced where and when cosmic structures could form. Rather than proceeding uniformly across space, structure formation became clustered and episodic, concentrated, in regions with the right conditions for gas collapse. The deaths of the first stars added new dimensions to this influence. When population 3 stars exploded as supernovae after their brief lives, they released tremendous energy into their surroundings. These explosions sent shock waves racing outward, compressing gas in their paths and potentially triggering new episodes of collapse. A single population 3 supernova could affect gas dynamics across tens of thousands of light-years, a significant fraction of the distance between early protogalaxies. In regions where multiple supernovae occurred relatively close together, their shock waves could interact, creating complex patterns of compression and rarefaction that further shaped the distribution of matter. These explosive events also ejected matter at high velocities, redistributing mass across cosmic scales. The most energetic population 3 supernova pair instability supernovae from stars between 140 and 260 solar masses could expel most of their mass back into intergalactic space, where it would eventually contribute to the formation of new cosmic structures. Perhaps the most significant long-term influence came through chemical enrichment. When the first stars died, they scattered newly forged elements carbon, oxygen, silicon, iron, and more across space. This chemical enrichment fundamentally changed the physics governing subsequent structure formation. Gas enriched with metals can cool much more efficiently than pristine hydrogen and helium. Metal atoms and ions provide additional ways for gas to lose energy through radiation, allowing it to cool faster and collapse more readily. This enhanced cooling efficiency altered the typical masses of structures that could form. While pristine gas tended to collapse into relatively massive objects, the mini-halos that hosted the first stars had about 100 times the sun's mass-enriched gas could form smaller structures. This shift towards smaller scales influenced the mass spectrum of cosmic structures, from stars to galaxy clusters. The distribution of metals was not uniform across space. Regions near population 3 supernovae received higher levels of enrichment, while more distant areas remained relatively pristine. This chemical patchiness created a diversity of environments with different structure-forming capabilities, contributing to the rich variety of cosmic structures we observe today. Over time, as more stars lived and died, metals were distributed more widely and homogeneously. But the initial patterns of enrichment established by the first stars influenced where the first substantial protogalaxies could form and how efficiently they could convert gas into stars. The first stars also affected cosmic structure through their influence on dark matter, the mysterious substance that outweighs ordinary matter by about 5-to-1 in our universe. While dark matter doesn't interact with light or participate in chemical processes, it responds to gravity from all matter, including that affected by the first stars. As radiation and supernova explosions from the first stars redistributed ordinary matter, the gravitational potentials governing dark matter's distribution also shifted. This coupling between ordinary and dark matter helped establish the foundation of the cosmic web, the network of filaments, sheets, and voids that characterizes large-scale structure. Computer simulations reveal how these processes unfolded. By modeling the physics of the early universe, from the expansion of space to the collapse of gas clouds to the lives and deaths of the first stars, researchers can trace how initially small density fluctuations evolved into the complex structures we observe today. These simulations show that the influence of the first stars created a kind of cosmic feedback loop. Regions where stars formed first affected neighboring regions through radiation, explosive energy, and chemical enrichment. These effects then influence where subsequent stars could form, creating a cascade of cause and effect that shaped emerging cosmic structure. The James Webb Space Telescope is now giving us direct glimpses of this process in action. By observing galaxies that formed in the first few 100 million years after the Big Bang, it reveals how quickly cosmic structure emerged from the relatively smooth early universe, and how the first generations of stars influenced this evolution. These observations show that significant structure formed earlier than many models had predicted, suggesting that the first stars and their effects may have accelerated structure formation in some regions. The detection of surprisingly mature galaxies just 300-400 million years after the Big Bang indicates that the transition from isolated stars to organized collections must have proceeded rapidly in some areas. We can also trace the first star's structural influence by studying chemical patterns across different cosmic environments. By mapping the distribution of elements in and around galaxies, astronomers can reconstruct aspects of their formation history, including the influence of early stellar generations. For example, our Milky Way's oldest stars show distinctive chemical patterns that vary depending on their locations within the galaxy. Stars in the inner halo display different abundance signatures than those in the outer halo, reflecting different enrichment histories. These patterns provide clues about how our galaxy assembled from smaller structures, each with its own chemical evolution, driven by generations of stars dating back to the cosmic dawn. The influence of the first stars on cosmic structure extends to the intergalactic medium, the vast spaces between galaxies. This diffuse gas bears chemical and thermal imprints from billions of years of stellar activity, beginning with the first generation. By studying absorption features in the spectra of distant quasars as their light passes through this medium, astronomers can map these imprints across cosmic time. These observations reveal that the intergalactic medium contains metals even in relatively low-density regions far from galaxies, indicating that stellar influences, likely beginning with energetic population 3, supernova Have, reached even these remote areas. The distribution of these metals provides information about how energy and matter have flowed between galaxies and the intergalactic medium throughout cosmic history. On the largest scales, the first stars helped establish the foundations of cosmic homogeneity and isotropy observation that, when viewed over sufficiently large distances, the universe appears roughly similar in all directions and locations. By helping regulate the efficiency of structure formation through feedback processes, they contributed to the statistical uniformity we observe in the distribution of galaxies and larger structures. Yet they also contributed to cosmic variance, the observation that structure formation proceeded at different rates in different regions. The stochastic nature of where the first stars formed and how they influenced their surroundings created variations in how quickly structure emerged across the cosmos. These variations are visible today in the somewhat uneven distribution of galaxy clusters and superclusters across the observable universe. The structural legacy of the first stars connects directly to questions about our own cosmic environment. Our Sun formed in a spiral galaxy that assembled from smaller components over billions of years, each influenced by stellar generations dating back to the cosmic dawn. The structure of our galaxy, its disk, bulge, halo, and satellite system, reflects this long history of hierarchical assembly, with the first stars playing a foundational role. Even Earth's position within this structure is not entirely disconnected from the first star's influence. Our solar system formed in a spiral arm of the Milky Way, in a region with a particular chemical composition resulting from billions of years of stellar evolution. This composition influenced the architecture of our planetary system, including Earth's size, composition, and potential habitability. As we continue developing more sophisticated observational tools and simulation capabilities, our understanding of how the first stars shaped cosmic structure will continue deepening. The James Webb Space Telescope is systematically pushing our observational horizon back toward the era of the first stars, while next-generation supercomputers enable increasingly detailed and physically complete simulations of early cosmic evolution. These advances promise to gradually fill in the remaining gaps in our understanding of how the universe transitioned from the relative simplicity of its early stages to the rich structural complexity we observe today, transition in which the first stars played a pivotal role. The story of how the first stars shaped cosmic structure is ultimately a story of how complexity emerged from simplicity, how homogeneity gave way to diversity, and how the actions of individual phenomena collectively produced patterns that persist to the present day. It connects the physics of nuclear fusion inside stellar cores to the grandest scales of cosmic architecture, demonstrating the profound interconnectedness of processes operating across vastly different scales of size and time. In the scattered light of those first stellar giants, the universe began its journey from uniformity to structure, from simplicity to complexity, from isolation to connection. Though they lived and died long before galaxies like our Milky Way took shape, the first stars helped establish the foundations upon which all subsequent cosmic evolution would build. Their light didn't just illuminate the darkness, it helped sculpt the very architecture of our universe. Chapter 11. Could some first stars still exist? Is it possible that somewhere in our vast universe, a first-generation star still shines after nearly 14 billion years? This tantalizing question challenges our understanding of stellar lifespans and the early universe. While most population 3 stars likely perished long ago, certain theoretical scenarios leave open the possibility that a few might have survived to the present day. The conventional narrative about population 3 stars emphasizes their massive size and brief existence. Most models suggest these primordial giants typically had masses between 40 and 300 times that of our Sun. Such massive stars burn through their nuclear fuel at prodigious rates, living just 2 to 3 million years before dying in spectacular supernovae. If all first stars fit this description, none could possibly remain today, having exhausted their fuel billions of years before our solar system even formed. However, star formation is an inherently complex and probabilistic process. Even in the early universe, with its different physics and chemistry, the collapse of primordial gas clouds likely produced stars with a range of masses, albeit weighted toward the higher end of the spectrum. This is where an intriguing possibility emerges. If some population 3 stars formed with masses below about 0.8 solar masses, they could theoretically survive until the present day. Stars of this size burn their hydrogen extremely slowly and efficiently. A 0.8 solar mass star has a theoretical lifespan of approximately 15 billion years longer than the current age of the universe. A 0.5 solar mass star could shine steadily for over 50 billion years. But could such low-mass population 3 stars have formed at all? This question sits at the intersection of theoretical astrophysics, computational modeling, and observational constraints. The primary challenge to low-mass population 3 star formation was cooling efficiency. Without metals to radiate away heat, primordial gas clouds couldn't cool and fragment as readily as gas in the contemporary universe. This inefficient cooling biased early star formation toward larger masses. A gas cloud needed to accumulate significant mass before gravity could overcome thermal pressure and trigger collapse. However, several theoretical models suggest pathways by which some low-mass population 3 stars might have formed. One possibility involves fragmentation during the collapse of rotating primordial gas clouds. As these clouds contracted and spun faster due to conservation of angular momentum, they could form disk-like structures. These disks might become unstable and fragment into smaller clumps, potentially including some low-mass stars. Another mechanism involves the effects of turbulence in collapsing primordial clouds. Turbulent flows can create local density enhancements, where smaller masses of gas might collapse independently. Sophisticated three-dimensional simulations show that under certain conditions, this process could form stars with masses as low as 0.1 to 0.5 solar masses, even from pristine primordial gas. A third scenario involves the influence of radiation from the first massive stars on nearby gas clouds. This radiation could ionize the gas, changing its cooling properties and potentially enabling the formation of lower-mass stars in the vicinity of their massive counterparts. The possibility of low-mass population 3 star formation receives some support from observations of present-day star formation, which produces a wide spectrum of stellar masses from a single molecular cloud. While the conditions were certainly different in the early universe, the fundamental physical processes governing gravitational collapse, fragmentation, and accretion have remained consistent throughout cosmic history. If low-mass population 3 stars did form, where might they be found today? The most likely location would be the halo of our Milky Way Galaxia spherical region, surrounding the familiar disk where we find the Sun. The galactic halo contains the oldest stars in our galaxy, orbiting in random orientations that take them far above and below the disk. These ancient halo stars include extremely metal, poor, EMP, objects with less than 1/10,000th the metal content of our Sun. But true population 3 stars would be even more extreme, having essentially zero metals except for tiny amounts they might have accumulated from their surroundings over billions of years. Detecting such objects presents extraordinary challenges. Low-mass population 3 stars would be intrinsically faint due to their small size. Their great age means they would likely be located in the outer reaches of the galactic halo, at distances of perhaps 100 light-years or more from Earth. And distinguishing them from second-generation stars that are merely extremely metal-poor requires exceptionally precise measurements. Despite these challenges, astronomers have conducted several systematic searches for surviving population 3 stars. These searches typically involve first identifying candidate stars with very low metal content through wide-field surveys, then conducting detailed follow-up spectroscopy to precisely measure their chemical compositions. So far, no confirmed population 3 star has been discovered. The most metal-poor stars found to date, like SMSS J31000, 300.36 670,000, 839.3 mentioned earlier, still show detectable levels of elements like carbon that indicate they formed from gas enriched by previous stellar generations. But as observational capabilities improve, these searches continue with increasingly sophisticated techniques. The James Webb Space Telescope might contribute to this quest indirectly. By studying the earliest galaxies, it could provide better constraints on the initial mass function of the first stars and the extent to which low-mass stars might have formed among them. This contextual information would help guide future searches for surviving population 3 stars in our galactic neighborhood. Beyond our own galaxy, low-mass population 3 stars might exist in other ancient structures like globular clusters or small dwarf galaxies. Some of these systems formed very early in cosmic history and have evolved with minimal external influences, potentially preserving specimens from the earliest stellar generations. Ultra-faint dwarf galaxies orbiting the Milky Way are particularly promising hunting grounds. These small, dim systems contain just a few thousand to a few million stars, making complete spectroscopic surveys feasible. Some have chemical patterns suggesting they experienced very few generations of star formation before their activity was halted, potentially preserving stars from the earliest cosmic epochs. If we did discover a genuine surviving population 3 star, it would represent an extraordinary scientific treasure. Such an object would provide direct insights into the conditions of the early universe cosmic time capsule, preserving information about the universe's chemical state before stars began enriching it with heavier elements. Spectroscopic analysis of such a star would reveal the exact abundance patterns of elements created in the Big Bang, primarily hydrogen and helium, with trace amounts of lithium. This would provide crucial constraints on models of Big Bang nucleosynthesis and potentially resolve discrepancies between theoretical predictions and current observational estimates of primordial element abundances. A surviving population 3 star would also serve as a laboratory for studying stellar physics under extreme conditions. How does a star function with essentially zero metals? How does the absence of elements like carbon, nitrogen, and oxygen, which catalyze important fusion processes in modern stars, affect its internal dynamics? Direct observation would answer questions that currently can only be addressed through theoretical models. The age of such a star, nearly 14 billion years, would also make it valuable for chronological studies. Techniques like astroseismology, which analyzes oscillations in a star's structure, can provide age estimates independent of chemical composition. This could offer new constraints on the universe's age and the timeline of early cosmic events. Even if no true population 3 stars have survived, the search for them yields valuable scientific insights. By systematically analyzing the most metal-poor stars currently observable, astronomers develop increasingly precise constraints on when and how the first stellar generations enriched the pristine universe with heavier elements. These extremely metal-poor stars represent the next best thing to observing population 3 stars directly. They formed from gas enriched by just one or a few first-generation supernovae, preserving relatively undiluted chemical signatures from the earliest stellar explosions. By studying patterns across many such stars, researchers can reconstruct aspects of the first stellar population, even without direct observations. This approach has already yielded important discoveries. For example, the unusual abundance patterns in some extremely metal-poor stars suggest that the first supernovae had different properties than typical explosions today. Some show evidence of fall back, where the innermost layers of stellar material fall back onto the remnant rather than being ejected. Others hint at explosions that were asymmetric or that occurred in rapidly rotating stars. The study of these chemical fossils also provides insights into how quickly the universe became enriched with heavier elements and how uniformly this enrichment proceeded. The diversity of chemical patterns observed in ancient stars indicates that early enrichment was patchy, with significant variations from one region to another. This patchiness influenced subsequent cosmic evolution, potentially affecting where and when the first substantial protogalaxies could form. Even if the search for surviving population 3 stars ultimately confirms that none exist, it would still provide valuable constraints on early star formation. Confirming the absence of low-mass first-generation stars would support models predicting a top-heavy initial mass function in the metal-free early universe. This would help refine our understanding of how star formation processes change under different conditions. The question of surviving first stars connects to broader themes in cosmology and stellar evolution. It challenges us to consider the full diversity of outcomes possible in early cosmic history, rather than focusing solely on the typical or average case. It reminds us that stars, like other natural phenomena, likely formed with statistical distributions of properties, rather than all conforming to a single template. This perspective has implications beyond the specific question of population 3 survivors. It encourages researchers to consider unusual or edge cases in other aspects of cosmic evolution, rare events or objects that might have had disproportionate influences on subsequent development. The history of astronomy is filled with instances where seemingly exceptional objects provided crucial insights into fundamental processes. As our observational capabilities continue advancing, the search for surviving population 3 stars will employ increasingly powerful tools. The upcoming Extremely Large Telescope, with its 39-meter primary mirror, will be able to obtain high-resolution spectra from much fainter stars than currently possible, potentially revealing chemical signatures too subtle to detect with existing facilities. The Roman Space Telescope, formerly WFIRST, will conduct unprecedentedly wide surveys that could identify new candidate extremely metal-poor stars for follow-up study. Its infrared sensitivity will allow it to peer through dust and observe stars in previously obscured regions of our galaxy, potentially including ancient specimens in the innermost halo. These observational advances will be complemented by increasingly sophisticated theoretical models and simulations. As computational power grows, researchers can model primordial star formation with greater physical completeness, higher resolution, and larger statistical samples. These improvements help constrain the probability of low-mass population 3 star formation and guide observational searches. The upcoming generation of exascale supercomputers will enable simulations that follow the collapse of primordial gas clouds with unprecedented detail, resolving the fine-scale processes that might lead to fragmentation and low-mass star formation. By simultaneously modeling many such clouds with slightly different initial conditions, researchers can better assess the statistical likelihood of various outcomes. These simulations are already revealing new possibilities. Some recent models suggest that under certain conditions involving strong radiation fields, primordial gas might form stars with masses as low as 0.1 solar masses objects that would easily survive to the present day. Other simulations explore how binary or multiple star systems might have formed in the early universe, potentially including low-mass companions to massive primary stars. The question of surviving population 3 stars also connects to broader themes in our understanding of cosmic history. It highlights the tension between typical patterns and rare exceptions, between dominant processes and edge cases. While most matter in the early universe likely processed through massive, short-lived stars, small pockets might have followed different evolutionary paths. This perspective aligns with our growing recognition of cosmic evolution's diversity and complexity. Rather than proceeding uniformly across space and time, processes like star formation, chemical enrichment, and structure development occurred at different rates and with different outcomes in different regions. This diversity created the rich cosmic ecosystem we observe today. The search for surviving first stars exemplifies how astronomers investigate questions where direct evidence is elusive or ambiguous. By combining theoretical models, computational simulations, and systematic observations, researchers gradually constrain possibilities and narrow uncertainties, even when definitive answers remain beyond immediate reach. This methodical approach has gradually shifted the consensus on low-mass population 3 stars. While earlier models suggested they were highly improbable, more recent work indicates they might have formed in limited numbers under specific conditions. This evolution in scientific thinking demonstrates how our understanding of the early universe continues to develop through the interplay of theory and observation. The possibility of surviving first stars also sparks the imagination, connecting us to the universe's earliest epochs. These hypothetical objects would be the oldest surviving structures in our Cosmos Elder witnesses to nearly 14 billion years of cosmic evolution. They would have formed when the universe was less than 1% of its current age, in an environment profoundly different from anything we can directly observe today. If such stars exist, they carry within them the memory of a universe without galaxies, without planets, without most of the elements that comprise our bodies and our world. They formed from matter that had never been part of a star before, pristine material directly from the aftermath of the Big Bang. They would be cosmic living fossils of incalculable scientific value. The search for these ancient survivors continues, driven by both scientific curiosity and the technical challenges that make their detection so difficult. Each new survey that pushes the boundaries of observable stellar chemistry brings us closer to either discovering these elusive objects or establishing firmer constraints on their potential existence. Whether or not any population 3 stars have survived to the present day, the question itself illuminates important aspects of cosmic evolution. It challenges simplistic narratives about the early universe and reminds us of the diversity of processes operating even in seemingly uniform conditions. It connects the physics of stellar formation and evolution to the grandest scales of cosmic history and structure. And perhaps most profoundly, it reminds us of our connection to cosmic history. If low-mass population 3 stars do exist, they would be our most ancient stellar relatives, distant cousins to our Sun, formed from the same primordial hydrogen, but following a different evolutionary path. They would embody the continuity between the universe's first moments and our own existence, linking cosmic dawn to the present day through the enduring presence of nuclear fusion transforming hydrogen into helium, the process that has illuminated our universe for nearly 14 billion years. The question of surviving first stars thus represents more than an astronomical curiosity. It touches on fundamental themes of continuity and change, of dominance and rarity, of the relationship between typical patterns and exceptional cases. It challenges us to balance theoretical expectations with observational constraints, to consider both what likely happened and what might have happened in our universe's infancy. As we continue searching the heavens for these ancient luminaries, we deepen our connection to cosmic history and expand our understanding of how the universe evolved from primordial simplicity to the rich complexity we observe today. Whether or not we ultimately find surviving population 3 stars, the quest itself enriches our perspective on stellar evolution and cosmic development. And if, someday, astronomers do identify a genuine first-generation star still shining after nearly 14 billion years, it would represent one of astronomy's most profound discoveries, direct window into the universe's infancy, and a living relic of the cosmic dawn. Until then, the possibility remains a compelling reminder of how much we still have to learn about our universe's earliest epochs and the diversity of outcomes possible within the laws of physics operating across cosmic time. Some researchers have proposed more creative approaches to detecting potential population 3 survivors. One idea involves searching for signs of accretion from the interstellar medium. Over billions of years, even a star with initially 0 metals would have traveled through space containing trace amounts of elements heavier than helium. Some of this material might have been accreted onto the star's surface, potentially creating a thin veneer of metals over an otherwise pristine composition. This scenario creates a distinctive observational signature, a star with an extremely low but non-zero metal content, where the metals are concentrated in the outermost layers rather than being uniformly mixed throughout. Sophisticated spectroscopic analysis might be able to distinguish this pattern from the more uniform distribution expected in genuine second-generation stars. Another approach focuses on unusual isotope ratios. Different processes of nuclear synthesis produce different isotopes of elements. The unique conditions inside population 3 stars and their supernovae would have created isotope ratios distinguishable from those produced by later stellar generations. Even if a surviving first star has accreted some metals from its surroundings, isotopic analysis might reveal its true primordial nature. The search extends beyond our own galaxy. Nearby dwarf galaxies, particularly those that appear to have formed in isolation with minimal influence from larger galaxies, might preserve specimens from the earliest stellar generations. Some of these systems show evidence of very simple chemical evolution, suggesting they experienced just a few episodes of star formation before becoming dormant. Intergalactic stars, those found in the vast spaces between galaxies, represent another potential habitat for ancient stellar fossils. Ejected from galaxies through gravitational interactions or formed in isolation from primordial gas, these stars might have evolved with minimal external influences. Detecting them presents enormous challenges due to their distance and faintness, but future facilities might bring them within observational reach. The quest to find surviving population 3 stars exemplifies how astronomy connects theory, observation, and computation to investigate questions about our deepest cosmic origins. It demonstrates the value of searching for exceptional objects, those that fall outside typical patterns, but might provide unique insights into fundamental processes. Whether or not any first-generation stars have survived to the present day, their legacy continues through the elements they created, the cosmic structures they influenced, and the scientific questions they inspire. They represent our most direct connection to the universe's infant scythe, the first link in a chain of stellar generations that ultimately led to our own existence in a complex, chemically diverse cosmos. Chapter 12. The Universe Before Galaxies. What did the cosmos look like before the first galaxies formed? If we could somehow transport ourselves back to this primordial era, what would we see spreading out around us? The universe before galaxies was a place fundamentally different from the cosmic landscape we observe today, transitional realm between primordial simplicity and emerging complexity. To understand this pivotal period in cosmic history, we need to journey back approximately 13.5 billion years to a time when the universe was just a few 100 million years old. The cosmos had already undergone several profound transitions since the Big Bang, each reshaping its fundamental nature. The universe began in an extraordinarily hot, dense state. During its first few minutes, it cooled enough for protons and neutrons to combine into the nuclei of light elements, primarily hydrogen and helium, with trace amounts of lithium. For about 380 years, the universe remained an opaque plasma, where light could not travel freely due to constant scattering off free electrons. Then came a moment astronomers call recombination or decoupling. As the expanding universe cooled below about 30 Kelvin, electrons combined with nuclei to form neutral atoms. Suddenly, photons could travel unimpeded for the first time. This released the cosmic microwave background radiation, the oldest light we can observe, which continues traveling through space today. After recombination, the universe entered the cosmic dark ages. No stars yet existed to generate new light. The only electromagnetic radiation present was the gradually cooling afterglow of the Big Bang, which quickly shifted from visible light to infrared and then to radio waves as the universe continued expanding. During these dark ages, lasting for perhaps 100 million years, the universe was filled with neutral hydrogen and helium gas, distributed almost but not quite uniformly across space. The slight variations in density, just 1 part in 100, had been imprinted by quantum fluctuations in the earliest moments after the Big Bang, then amplified during a period of rapid expansion called inflation. These tiny density differences would prove crucial for cosmic evolution. In slightly denser regions, gravity began drawing more matter inward. In slightly less dense regions, matter gradually flowed outward. This process, the growth of structure under gravity's influence, proceeded slowly at first, but accelerated as differences became more pronounced. By about 100 to 200 million years after the Big Bang, some regions had grown dense enough for the first step towards structure, the formation of mini-halos. These concentrations of dark matter and gas contained perhaps 100 times the mass of our Sun. Within these mini-halos, gas began to cool and condense further through the formation of molecular hydrogen, which could radiate away energy more efficiently than atomic hydrogen. This cooling allowed the gas in some mini-halos to collapse to even higher densities, eventually reaching the conditions necessary for nuclear fusion. At this point, perhaps 180 million years after the Big Bang, the first stars ignited, ending the cosmic dark ages. If we could observe the universe at this moment, before galaxies, but after the first stars had formed, what would we see? The most striking feature would be the darkness, interrupted by isolated, brilliant points of blue-white light. These first stars, population 3 stars, were predominantly massive giants, perhaps hundreds of times more massive than our Sun. They burned hot and bright, emitting intense ultraviolet radiation that began ionizing nearby hydrogen. Unlike stars today, which typically form in clusters within galactic structures, these first luminaries appeared as solitary beacons, or in small, sparse groups. They were scattered across cosmic space wherever conditions first became suitable for their formation, primarily at the nodes where filaments of the emerging cosmic web intersected. Around each star, an expanding bubble of ionized hydrogen would be visible regions where the star's ultraviolet radiation had stripped electrons from hydrogen atoms. These ionization bubbles appeared as spheres of hot, glowing plasma surrounding each stellar source. As these bubbles expanded and occasionally merged, they created the first distinct structures in the post-recombination universe. The distribution of these first stars wasn't entirely random. They preferentially formed in regions that were slightly denser than average, the peaks in the primordial density field that had been growing under gravity's influence since recombination. This created a subtle pattern in their distribution, tracing the underlying variations in density that would eventually grow into the cosmic web of filaments and voids. Between these scattered stellar beacons, vast regions remained dark and largely unchanged still, filled with the primordial neutral hydrogen that dominated the cosmic inventory. In these unilluminated regions, gas continued flowing along density gradients, gradually enhancing the contrast between emerging structures. The universe at this stage had a haunting beauty of darkness, interrupted by brilliant but isolated sources of light, each surrounded by its glowing ionized nebula. It was a cosmos in transition, no longer the uniform sea of neutral gas from the Dark Ages, but not yet organized into the familiar cosmic structures we see today. As the first stars evolved through their brief life cycles, living perhaps only 2 to 3 million years, the landscape began changing again. Some of these massive stars ended their lives as energetic supernovae, sending shockwaves racing outward and scattering newly forged heavy elements across space. These explosions added new visual elements to the cosmic scene, expanding shells of hot, glowing gas, enriched with the first carbon, oxygen, silicon, and other elements heavier than helium. These supernova remnants would have been visible as roughly spherical structures, often hundreds of light years across, gradually cooling and merging with the surrounding medium. The influence of these first stars and their supernovae began reshaping the cosmic environment. Radiation pressure pushed against gas, creating voids and compressing material into denser filaments. Shockwaves from supernovae triggered new episodes of gas collapse in some regions, while disrupting potential star formation in others. The first heavy elements changed the cooling properties of gas, allowing it to collapse more efficiently in regions that had been enriched. Around 200 to 500 million years after the Big Bang, these processes began driving the next major transition, the formation of the first substantial stellar groupings that would eventually become protogalaxies. Gas continued flowing along filaments toward the densest nodes, which had been further enhanced by the effects of the first stars. In these dense regions, new stars began forming at an accelerated rate. Unlike the first generation, these new stars formed from gas that had been at least lightly enriched with metals from the first supernovae. This changed their properties. They could form with a wider range of masses, including smaller, longer-lived stars alongside massive giants. As these stellar groupings grew, they began exhibiting properties we might recognize as primitive galactic structures. They concentrated enough mass to create substantial gravitational wells that attracted more gas along cosmic filaments. They contained multiple generations of stars with different properties and ages, and they began developing internal dynamics, with stars and gas orbiting around common centers of mass. But these emerging protogalaxies were not yet the ordered spiral or elliptical structures we see today. They were irregular, chaotic collections of stars embedded in gas clouds, perhaps resembling scaled-down versions of the dwarf irregular galaxies in our local cosmic neighborhood. The transition from isolated stars to the first protogalaxies did not occur uniformly across the cosmos. In some regions, those with initially higher densities protogalaxies began assembling relatively early, perhaps 300 to 400 million years after the Big Bang. In other regions, with lower initial densities, Isolated star formation continued for hundreds of millions of years before substantial structures began forming. This asynchronous development created a patchwork universe where different regions had reached different stages of evolution simultaneously. An observer traveling across cosmic distances would have encountered zones with just a few isolated stars, regions where small stellar groups were beginning to coalesce, and areas where substantial protogalaxies were already actively forming new stars. The large-scale pattern of cosmic structure was also becoming more pronounced during this period. The subtle density variations present since the earliest moments had been amplified by gravity and the effects of the first stars. A cosmic web of filaments, sheets, and voids was emerging, with matter flowing away from underdense regions and toward overdense ones. Dark matter played a crucial role in this structural evolution. This mysterious substance, which interacts through gravity but not through electromagnetic forces, had begun clustering earlier than ordinary matter. It formed halos of various sizes that provided the gravitational scaffolding around which visible structure would organize. By approximately 500 million to 1 billion years after the Big Bang, many regions had transitioned from isolated stars to genuine protogalaxies. These early galactic systems were typically small by today's standards, perhaps containing a few million to a billion stars, compared to the hundreds of billions in our Milky Way. If we could observe the universe at this stage, we would see the cosmic web coming into sharper focus, with young protogalaxies concentrated along filaments and especially at their intersections. Between these structures, vast cosmic voids would be growing as matter continued flowing outward toward denser regions. The formation of these early galactic systems accelerated cosmic reionization. While individual population 3 stars had begun ionizing their surroundings, the collective ultraviolet output from star-forming protogalaxies increased the pace dramatically. By approximately 1 billion years after the Big Bang, most hydrogen in the intergalactic medium had been reionized, fundamentally changing the environment in which further structure formation would occur. This array, the transition from first stars to first galaxies, represents a pivotal chapter in cosmic history. It was when the universe first began developing the hierarchical structure that characterizes it today, when isolated phenomena began organizing into collective systems with new properties and capabilities. The James Webb Space Telescope is now giving us direct glimpses of this transformative period. By observing infrared light that has traveled for more than 13 billion years, it captures images of protogalaxies forming when the universe was just a few 100 million years old. These observations confirm aspects of our theoretical understanding while challenging others, revealing a universe that developed structure earlier and more rapidly than many models had predicted. What drove this transition from a universe of isolated stars to one organized into galaxies? Several interconnected processes contributed. First, gravity continued drawing matter toward overdense regions, with each generation of structure creating deeper gravitational wells that attracted more material. The formation of the first stars enhanced this process by adding their gravitational influence to that of the underlying dark matter. Second, the deaths of the first stars scattered heavy elements that changed the physics of subsequent structure formation. Gas enriched with these metals could cool more efficiently, allowing it to collapse more readily and form stars with a wider range of masses. This chemical enrichment accelerated structure formation by enabling more efficient conversion of gas into stars. Third, radiation and kinetic energy from the first stars and their supernovae created pressure gradients that helped shape the distribution of gas. By heating some regions while compressing others, these feedback processes influenced where subsequent generations of stars could form, helping concentrate star formation in certain regions while suppressing it in others. Fourth, the continuing expansion of the universe played a crucial role. As space expanded, the average matter density decreased, making it progressively more difficult for gas to collapse in regions that hadn't already begun forming structure. This effectively froze the pattern of emerging overdensities and underdensities, preventing new structures from forming in initially low-density regions. The interplay of these processes created the transition from a relatively uniform early universe to the richly structured cosmos we observe today. It was a period of accelerating complexity, with each generation of structure creating conditions that enabled the formation of the next. One of the most fascinating aspects of this era was its asynchrony across cosmic space. Different regions evolved at different rates, depending on their initial conditions and subsequent influences. This created a universe with multiple evolutionary stages simultaneously present a cosmic laboratory where processes separated by hundreds of millions of years in a single location could be observed operating concurrently across different regions. This variation continues in the present-day universe. When we observe very distant objects, we're looking back in time due to the finite speed of light. The most distant galaxies visible with our most powerful telescopes appear as they were when the universe was just a few 100 million years old, proto-galaxies still in their formative stages. Closer objects appear as they were more recently, showing more mature stages of galactic evolution. By systematically studying objects at different distances, and thus different cosmic epochs, astronomers can reconstruct how structure emerged and evolved over billions of years. This approach has revealed that galaxy formation wasn't a one-time event, but an ongoing process that continues to the present day, albeit at a slower pace in our more mature universe. The story of cosmic structure formation connects to fundamental questions about order and complexity in our universe. How did a cosmos that began in an extraordinarily hot, dense, nearly uniform state develop the rich hierarchical structure we observe today? What roles did deterministic physical laws and random fluctuations play in shaping this evolution? The answer appears to lie in the interplay between initial conditions and subsequent physical processes. The seeds of structure were planted in the earliest moments of cosmic history, quantum fluctuations magnified by inflation to macroscopic scales. But the specific pattern of cosmic structure that emerged depended on how these seeds grew under the influence of gravity, radiation, gas dynamics, nuclear fusion, and other processes operating over billions of years. The universe before galaxies was a crucial transitional stage in this evolutiono, longer than nearly uniform sea of matter from the earliest epochs, but not yet organized into the familiar structures we see today. It was a time when complexity was emerging from simplicity, when hierarchy was developing from uniformity, when the cosmic stage was being set for all that would follow. This period is particularly fascinating because it represents the universe's adolescentia, time of rapid change and development between the simplicity of cosmic childhood and the relative maturity of later epochs. Like biological adolescence, it was characterized by growth spurts, awkward transitions, and the emergence of adult characteristics in a still developing system. The universe before galaxies was also the setting for several cosmic firsts: the first stars, the first supernovae, the first black holes, the first heavy elements. These pioneering phenomena established patterns and processes that would continue throughout cosmic history. They were the universe's first experiments with structure and complexity, the initial steps toward the rich cosmic ecosystem we inhabit today. As we push our observational capabilities further back in time, we edge closer to witnessing this formative period directly. The James Webb Space Telescope is already revealing galaxies from when the universe was less than 400 million years old. Future facilities like the Extremely Large Telescope and the Square Kilometre Array promise to push these observations even earlier, potentially detecting the light from the first stars and mapping the distribution of neutral hydrogen during the cosmic dawn. These observations will help answer lingering questions about this pivotal era. When exactly did the first stars form, and what was their typical mass? How quickly did they enrich their surroundings with heavy elements? How did they influence subsequent structure formation through radiation, kinetic energy, and chemical enrichment? How did the first substantial protogalaxies assemble from these stellar building blocks? What's already clear is that this period represents one of the most significant transitions in cosmic history, from a universe dominated by individual phenomena to one characterized by collective systems. It was when the universe first began resembling the place we recognize today, with matter organized into hierarchical structures rather than distributed nearly uniformly across space. This transition reflects a broader pattern observed throughout nature: the emergence of complexity from simpler components interacting through basic forces. Just as complex biological organisms arise from interactions among simpler molecular components, cosmic complexity emerged from interactions among matter and energy governed by fundamental physical laws. The universe before galaxies thus offers a cosmic perspective on the emergence of complexity, a theme that connects astronomy to other scientific disciplines, studying how organization arises at different scales. By understanding this formative period in cosmic history, we gain insights not just into astronomical phenomena, but into the broader processes through which complexity emerges throughout nature. This era also represents a crucial link in our own cosmic genealogy. The first stars created the initial batches of heavy elements necessary for planets and life. The transition to galactic structures established the environments in which subsequent stellar generations would form. These early developments set the stage for the eventual emergence of our Sun, our planet, and ultimately ourselves. When we look up at our star-filled sky with its visible galaxies, star clusters, and nebulae, we're seeing the mature outcome of processes that began during this formative period. The patterns of cosmic structure visible today had their origins in the transition from isolated stars to the first proto-galaxies, from a universe of scattered beacons to one organized into collective systems. The universe before galaxies was a place of darkness, punctuated by brilliant but isolated lights, of vast neutral hydrogen clouds gradually condensing under gravity's influence, of emerging complexity not yet organized into familiar forms. It was a universe in transition, no longer primordial, but not yet mature, finding its way from cosmic simplicity to the structured complexity that would eventually enable our existence. As we continue developing more powerful tools to study this era, we deepen our connection to our cosmic origins. We recover more chapters in the grand narrative that connects the Big Bang to the present day, the story of how our universe evolved from simplicity to complexity, from near uniformity to rich structure, from isolated phenomena to the interconnected cosmic ecosystem we inhabit today. The universe before galaxies represents the beginning of cosmic structure, the first steps in a journey that would eventually lead to spiral galaxies like our Milky Way, to planetary systems like our solar system, and ultimately to conscious beings capable of contemplating their own cosmic origins. When we study this pivotal era, we study a crucial chapter in our own creation story, the period when our universe first began organizing itself into the structures that would eventually make our existence possible. In this sense, the quest to understand the universe before galaxies is more than an astronomical curiosity. It's an exploration of our deepest cosmic roots. It connects us to the grand evolutionary arc that stretches from the Big Bang to human consciousness, helping us comprehend our place in the vast and ancient cosmos we call home. What makes this era particularly challenging to study is that it lies at the edge of observational accessibility. The light from these early cosmic structures has been traveling for more than 13 billion years, stretched by the expanding universe to wavelengths far beyond what our eyes can see. It comprises just a tiny fraction of the total light reaching Earth, easily overwhelmed by closer, brighter sources. Yet this feeble ancient light carries invaluable information about our cosmic origins. It records the moment when our universe first began developing the hierarchical structure that characterizes it today, the transition from primordial simplicity to emerging complexity. By capturing and analyzing this light with our most advanced telescopes, we recover crucial chapters in our universe's autobiography. The James Webb Space Telescope represents our most powerful tool for exploring this era. Its unprecedented infrared sensitivity allows it to detect galaxies from when the universe was just a few 100 million years old, approaching the time when the first substantial cosmic structures were forming from the light of solitary stars. These observations reveal a universe in transition, longer the nearly uniform expanse of the Dark Ages, but not yet fully organized into the familiar galactic patterns of later epochs. They show protogalaxies still in their formative stages, actively converting gas into stars and beginning to develop the characteristics that would define mature galaxies. Complementing these direct observations, computer simulations help fill gaps in our understanding. By modeling the physics of the early universe, from the expansion of space to the collapse of gas clouds to the lives and deaths of the first stars, researchers can trace how initially small density fluctuations evolved into the complex structures we observe today. These simulations show that the transition from isolated stars to the first protogalaxies likely occurred in stages, with multiple processes operating simultaneously. Gas continued flowing along filaments toward dense nodes, where star formation accelerated. Radiation and supernova explosions from the first stars influenced where subsequent generations could form, and chemical enrichment from stellar deaths changed the cooling properties of gas, allowing more efficient collapse in some regions. What emerges from both observations and simulations is a picture of cosmic adolescencia, period of rapid development between the simplicity of the early universe and the relative maturity of later epochs. Like biological adolescence, it was characterized by growth spurts, awkward transitions, and the emergence of adult characteristics in a still developing system. This adolescent universe was a place of extremes and contrasts. Brilliant stellar beacons interrupted vast dark regions. Primordial gas clouds coexisted with areas enriched by the first heavy elements. Individual stars shone in isolation, while the first small stellar groups began coalescing into primitive galactic structures. It was a universe finding its way from uniformity to complexity, from isolation to connection, from simplicity to structure. The patterns emerging during this period would eventually grow into the rich cosmic ecosystem we inhabit today, universe organized into galaxies, galaxy clusters, and the grand cosmic web that spans hundreds of millions of light years. When we study the universe before galaxies, we're exploring a crucial link in the chain connecting the Big Bang to our own existence. We're witnessing the first steps in cosmic self-organization, the beginning of the structural evolution that would eventually create environments suitable for planets and life. This perspective connects astronomy to broader questions about complexity and organization in nature. How does order emerge from less ordered states? How do simple components interacting through basic forces create complex systems with new properties? How does the arrow of cosmic evolution point from simplicity toward complexity? The transition from a universe of isolated stars to one organized into galaxies represents a cosmic example of emergence, the process by which complex systems and patterns arise from simpler interactions. It demonstrates how fundamental physical laws operating over time can transform a nearly uniform initial state into one rich with structure and hierarchy. How did the sequence of cosmic assembly unfold? In the narrative of our universe, stars were the protagonists that arrived before the setting was complete. They were the characters that appeared on stage while the theater was still being built around them. This reversal of what might seem the intuitive order structure first, then inhabitants represents one of the most fascinating aspects of our cosmic origin story. To appreciate the significance of this sequence, we need to understand how it differs from what we observe in the present-day universe. Today, stars form within the structured environments of galaxies. They condense from gas clouds in galactic disks, emerge in clusters within spiral arms, or appear in bursts triggered by galactic interactions. The galactic context comes first, stars second. But in the early universe, this sequence was inverted. The first stars formed before galaxies existed, in a cosmos that lacked defined structure. They didn't emerge within established galactic environments, but in isolation or small groups, scattered through a universe that was still developing its first architectonic forms. These pioneer stars didn't form randomly across space. They emerged primarily at the nodes of the embryonic cosmic web points, where filaments of slightly denser gas intersected. But these overdensities were subtle, representing perhaps just a 10% increase above the average cosmic density. They weren't the well-defined galaxies or clusters we see today, with densities thousands of times the cosmic average. What makes this inverted sequence so significant? First, it meant that stars themselves became active players in creating cosmic structure rather than merely inhabiting it. Their radiation, winds, explosive deaths, and chemical contributions helped shape how subsequent structure would form. They were architects as well as residents. Second, it established a pattern of bottom-up structure formation that would characterize cosmic evolution for billions of years to follow. Small structures formed first, then gradually assembled into larger ones. Individual stars preceded star clusters, which preceded proto-galaxies, which would later merge to form mature galaxies, which would eventually assemble into galaxy groups, clusters, and superclusters. This pattern reflects the influence of dark matter, the invisible substance that outweighs ordinary matter by about 5-to-1 in our universe. Dark matter began clumping under gravity's influence earlier than normal matter, forming halos of various sizes. The smallest halos formed first, with larger structures assembling progressively through mergers and continued accretion. The first stars emerged in mini-halos containing perhaps 0 times the Sun's mass in dark matter and a smaller amount of normal matter. These mini-halos were abundant in the early universe, forming wherever local density peaks were high enough to break away from the cosmic expansion and collapse under their own gravity. As these first stars illuminated the cosmos, they immediately began influencing their surroundings in ways that would shape subsequent structural development. Their intense ultraviolet radiation ionized nearby hydrogen, creating bubbles of hot plasma that expanded outward. These ionized regions had different physical properties than neutral gas. They were hotter, more resistant to compression, and interacted differently with radiation. When the first massive stars exploded as supernovae after their brief lives, they sent shock waves racing outward, compressing gas in some regions while heating and dispersing it in others. They scattered newly forged heavy elements across space, changing the cooling properties of gas and enabling more efficient collapse in regions that received this chemical enrichment. Through these processes, the first stars established feedback loops that would influence subsequent structure formation. In some regions, their effects accelerated structure development by compressing gas and enhancing cooling through chemical enrichment. In others, they temporarily suppressed further collapse by heating and ionizing the surrounding medium. This complex interplay created a self-regulating system that helped guide the transition from a relatively uniform early universe to the richly structured cosmos we observe today. Stars weren't passive spectators in this evolution, but active participants, helping shape the emergent pattern of cosmic structure. As more stars formed and their effects accumulated, the next level of cosmic structure began emerging, the first substantial stellar groupings that would eventually become protogalaxies. Gas continued flowing along filaments toward nodes where stars had already formed, attracted by their growing gravitational influence. In these regions, star formation accelerated, creating concentrations with dozens or hundreds of stars. Unlike the first, isolated population 3 stars, these growing stellar groups included second-generation stars formed from gas that had been enriched with metals from the first supernovae. These population 2 stars could form with a wider range of masses, including smaller, longer-lived stars alongside massive giants. This diversity created stellar populations with different properties and lifespans, adding new dimensions to cosmic complexity. As these stellar concentrations grew, they began developing characteristics we might recognize as primitive galactic structures. They contained enough mass to create substantial gravitational wells that attracted more gas along cosmic filaments. They developed internal dynamics, with stars and gas orbiting around common centers of mass. And they began influencing their surroundings on larger scales through collective radiation, stellar winds, and supernova explosions. This transition from isolated stars to the first protogalaxies represents a crucial phase in cosmic evolution. It marked the emergence of collective systems with properties beyond those of their individual components. These protostructures weren't simply groups of stars, but integrated systems where stars, gas, and dark matter interacted in complex ways, creating environments that would shape subsequent generations of stars. The sequence, stars first, galaxies second, had profound implications for how cosmic structure would develop. It meant that galaxies formed around pre-existing stellar populations rather than stars forming within already established galaxies. These initial stellar seeds influenced how their host protogalaxies would grow and evolve, establishing patterns that would persist for billions of years. For example, the first substantial star clusters likely formed at the centers of what would become protogalaxies. As these structures continued growing through gas accretion and mergers with other systems, these central stellar concentrations evolved into galactic bulges or nuclei. In the most massive systems, they would eventually host supermassive black holes, formed through the mergers of stellar mass black holes left behind by the first stars, or through direct gas collapse in regions of intense star formation. The narrative, stars first, structure second, also meant that the universe was already being chemically enriched while its structural hierarchy was still developing. By the time the first substantial protogalaxies formed, the gas from which they assembled was no longer pristine, but contained metals from previous stellar generations. This changed the physics of structure formation itself, allowing more efficient cooling and collapse, which in turn accelerated the pace of cosmic evolution. This chemical head start influenced the types of structures that could form. With more efficient cooling, gas could collapse into smaller units, enabling the formation of lower-mass stars and eventually planetary systems. The diversity of stellar masses increased, creating populations with a wide range of lifespans and evolutionary paths. Some stars formed with just the right mass and composition to eventually host habitable planets, setting the stage for the potential emergence of life. The James Webb Space Telescope is now giving us direct glimpses of this formative period. By observing infrared light that has traveled for more than 13 billion years, it captures images of the earliest substantial proto-galaxy structures that formed through the accumulation of stars and gas in the first few 100 million years after the Big Bang. These observations reveal systems still in their formative stages, actively converting gas into stars and beginning to develop the characteristics that would define mature galaxies. They show irregular, chaotic structures rather than the ordered spirals or ellipticals common in the later universe. Many appear surprisingly bright and massive for their cosmic age, suggesting that star formation and structural assembly proceeded more rapidly in some regions than standard models had predicted. What drove this accelerated development in certain cosmic locales? The answer likely lies in the distribution of those initial density fluctuations imprinted in the universe's earliest moments. Regions that started with slightly higher densities would form stars earlier and in greater numbers. These stars would then enhance their surroundings' density through gravitational attraction, while potentially accelerating further star formation through mechanisms like shock-induced collapse from supernova explosions. This created a kind of rich-get-richer scenario, where regions that formed stars first could accelerate their structural development, pulling ahead of cosmic regions that started with slightly lower densities. Over time, these differences amplified, creating the vast range of structural environments we observe today, from rich galaxy clusters containing thousands of galaxies to cosmic voids, nearly empty of substantial structure. The pattern, stars first, structure second, also influenced the timing and nature of cosmic reionization. The first stars began ionizing their surroundings as soon as they formed, creating isolated bubbles of plasma in the otherwise neutral cosmic medium. As more stars formed and these bubbles expanded and merged, large regions of intergalactic space became ionized. This process accelerated dramatically when the first substantial protogalaxies formed, concentrating many UV-emitting stars in relatively small volumes. These early galactic systems became the primary drivers of reionization, transforming the universe from neutral to ionized over the course of several 100 million years. By approximately 1 billion years after the Big Bang, most hydrogen in intergalactic space had been reionized, fundamentally changing the environment in which further structure formation would occur. This transition, driven by stars that formed before substantial galactic structures existed, altered the physics governing subsequent cosmic evolution, affecting everything from the typical masses of newly forming structures to the efficiency of gas cooling and collapse. The sequence, stars first, galaxies second, wasn't merely a chronological curiosity, but a fundamental pattern that shaped cosmic development. It established feedback loops between stellar activity and structural growth that would guide the universe's evolution for billions of years. It created a chain of cause and effect where each generation of structure influenced the formation of the next, building complexity through a series of interdependent steps. This narrative connects to broader themes about structure and organization in nature. Throughout the universe, we observe complex systems emerging from simpler components, interacting through basic forces. The transition from isolated stars to organized galaxies exemplifies this emergence of complexity, showing how relatively simple initial conditions can evolve into rich hierarchical structures through physical processes operating over time. The story also highlights the role of feedback in natural systems. The first stars didn't just passively witness the universe's structural evolution, they actively shaped it through their effects on surrounding gas. This established cycles of regulation, where stellar activity influenced subsequent structure formation, which in turn affected where and how later generations of stars would form. These feedback processes created a self-organizing system where order emerged not through external design but through the internal dynamics of matter and energy interacting under physical laws. The universe effectively organized itself from simplicity toward complexity, from uniformity toward structure, through processes inherent in its physical constitution. Exploring how stars preceded and shaped cosmic structure also informs our understanding of our own origins. The Sun formed approximately 4.6 billion years ago within a galaxy that had already experienced billions of years of structural evolution. But that galactic structure itself emerged from the accumulated influence of countless stars that came before reaching all the way back to the very first luminous objects. This connects us to the earliest chapters of cosmic history through an unbroken chain of cause and effect. The elements in our bodies were forged in stellar cores and scattered by supernovae, beginning with the first generations of stars. The galactic environment that enabled our solar system's formation developed through processes set in motion when stars first preceded structure. Even the physics that governs life on Earth operates within constraints established during cosmic dawn. As we develop more powerful observational tools and more sophisticated computer simulations, our understanding of this pivotal period continues deepening. The James Webb Space Telescope is systematically pushing our observational horizon back toward the era of the first stars, while next-generation supercomputers enable increasingly detailed and physically complete simulations of early cosmic evolution. These advances promise to gradually fill in the remaining gaps in our understanding of how the universe transitioned from the relatively uniform aftermath of the Big Bang to the rich structural complexity we observe today. Transition in which stars played the leading role, lighting the way for the cosmic structures that would follow. The story of how stars preceded and shaped structure also carries philosophical implications about order, complexity, and emergence in our universe. It suggests that complex organization doesn't necessarily require pre-existing structure, but can emerge from interactions among simpler components. It demonstrates how fundamental physical laws operating over time can transform relative uniformity into rich hierarchy through a series of interconnected steps. This perspective resonates with broader scientific narratives about emergence and self-organization across different scales, from the formation of molecules to the development of ecosystems, to the emergence of intelligence. In each case, complex systems arise from interactions among simpler components, with new properties and capabilities emerging at each level of organization. The specific sequence, stars first, structure second, also reminds us that cosmic evolution doesn't always follow what might seem the intuitive pattern. Just as stars formed before galaxies, other aspects of cosmic development have followed sequences that challenge straightforward expectations. Life on Earth, for instance, emerged relatively early in our planet's history, then spent billions of years in microscopic forms before more complex organisms evolved. This non-intuitive sequencing highlights the value of empirical investigation over assumptions based on current conditions. The present-day universe, where stars form within galactic environments, might suggest that galaxies should precede stars. But examination of the early universe reveals the opposite sequence, a reminder that systems evolve, and conditions in the past may have enabled processes that would be unlikely or impossible today. The pattern of stars preceding structure exemplifies how universal physical laws can produce different outcomes under different conditions. The same gravitational physics that causes gas to collapse into stars operates throughout cosmic history. But in the early universe, with its different density, temperature, and chemical composition, this collapse produced isolated stars first, then hierarchical structures. Today, with different background conditions, the same physics leads to star formation primarily within established galactic environments. This perspective helps us understand cosmic evolution as the application of consistent physical laws across changing conditions, rather than a series of disconnected episodes. It reveals the deep continuity underlying apparent differences between early and modern cosmic processes. The narrative, stars first, structure second, also carries implications for how we might understand the development of complexity in other contexts. It suggests that pioneers often emerge before the environments that will later nourish their descendants are fully formed. The first instances of new phenomena may appear in isolation, with supportive structures developing later in response to their influence. We can observe similar patterns in other evolutionary contexts. The first living organisms on Earth emerged in environments very different from those that support the biosphere today. The first human civilizations developed before many of the social and economic structures we now consider necessary for complex societies. In each case, pioneers helped shape the environments that would later become standard for their successors. This pattern reflects a fundamental aspect of evolutionary development. New forms often create conditions that support their own elaboration and diversification. The first stars changed their surroundings in ways that enabled more efficient formation of subsequent stellar generations. The first organisms altered Earth's chemistry in ways that supported more complex life forms. The first human settlements developed practices that enabled larger and more complex societies. In the cosmic context, understanding how stars preceded and influenced structure formation helps us appreciate the interconnectedness of phenomena across different scales. Individual nuclear fusion reactions inside stellar cores connect to galaxy formation processes operating across hundreds of thousands of light years. Local chemical enrichment from supernova explosions influences the development of cosmic structures spanning millions of light years. This multi-scale perspective reminds us that cosmic evolution involves processes operating simultaneously across vastly different dimensions, from the subatomic to the supergalactic. The universe doesn't develop in isolated compartments, but through the continuous interaction of phenomena across all scales of size, time, and complexity. The story of stars preceding structure also highlights the role of energy flows in creating and maintaining complex organization. The first stars represented concentrated energy sources in a universe that had previously lacked such localized centers. Their radiation, winds, and explosive deaths redistributed this energy across space, creating gradients and flows that helped shape emerging cosmic structure. This pattern energy concentration, followed by structured dissipation, appears in many complex systems. Living organisms concentrate energy through metabolism, then use it to maintain their organized state. Ecosystems develop structures that efficiently capture and distribute energy through food webs. Human civilizations harness energy sources to maintain social and technological complexity. In the cosmic context, stars represent the primary energy processing centers that drive structural development. They convert the potential energy of gravity into radiation, kinetic energy, and newly synthesized elements with higher binding energies. This energy conversion creates the conditions necessary for increasing complexity, from simple atomic structures to galaxies to planetary systems potentially capable of supporting life. The sequence stars first, structure second, thus connects to fundamental questions about how complexity emerges and evolves in our universe. It demonstrates how energy, concentration, and dissipation can drive the development of organization across different scales. It shows how local phenomena can influence global patterns through cascading effects. And it reveals how systems can develop hierarchical structure through the progressive assembly of components initially formed in isolation. As we continue exploring cosmic dawn with increasingly powerful observational and computational tools, we deepen our understanding of these processes. We trace how the first points of light in a dark universe initiated patterns of development that would eventually lead to the rich cosmic ecosystem we inhabit today. We discover the causal chains connecting the earliest stellar pioneers to the galactic structures they helped create and, ultimately, to our own existence in a complex, chemically diverse cosmos. The story of stars preceding structure thus offers more than an astronomical curiosity. It provides insights into fundamental processes of cosmic evolution, revealing how complexity emerges, how systems self-organize, and how initial conditions influence subsequent development. It connects the physics of stellar interiors to the grand architecture of the cosmic web, demonstrating the profound interconnectedness of phenomena across all scales of the universe. And perhaps most importantly, it links us to our deepest cosmic origins. When we study how the first stars shaped emerging structure, we're exploring essential chapters in our own creation story, the sequence of events that would eventually lead to our existence in a universe organized into galaxies, star systems, and planets capable of supporting life. In the darkness before cosmic dawn, the stage was set for a universe that would organize itself from simplicity toward complexity. The first stars were not merely the initial players in this cosmic drama, but active authors helping write the script that subsequent development would follow. They illuminated not just the primordial darkness, but the path toward the structured cosmos we inhabit today. a legacy written in light that continues shaping our universe, nearly 14 billion years after those first stellar beacons pierced the cosmic night. This perspective on stars' preceding structure carries implications for how we might understand cosmic habitability, the development of environments capable of supporting life. The sequence of stars forming before galaxies meant that chemical enrichment began very early in cosmic history, with the first heavy elements scattered across space hundreds of millions of years before substantial galactic structures had formed. This early start to chemical complexity created conditions where subsequent generations of stars could form with the materials necessary to produce rocky planets: the silicon, iron, oxygen, and other elements essential for terrestrial worlds. By the time the first substantial galaxies had assembled, significant chemical enrichment had already occurred, making these environments potentially capable of hosting habitable planets much earlier than might otherwise have been possible. Modern observations support this picture of early chemical enrichment. The James Webb Space Telescope has detected elements like oxygen in galaxies observed just 350–400 million years after the Big Bang, indicating that significant stellar processing of matter had already occurred by this early stage. This suggests that the basic chemical ingredients for potentially habitable planets were available relatively early in cosmic history. The pattern of stars' preceding structure also meant that stellar influences began shaping cosmic environments before galaxies were fully formed. Radiation from the first stars initiated the reionization of the universe, changing the physical state of matter across cosmic scales. Supernova explosions created pressure waves and injected energy into the primordial medium. These processes established feedback patterns that would influence subsequent galaxy formation and evolution. Within these emerging galactic environments, continued stellar activity created conditions necessary for planetary habitability. Supernova explosions concentrated heavy elements needed for rocky planet formation. Radiation from massive stars sculpted neighboring gas clouds, potentially triggering new episodes of star formation. Stellar winds helped regulate the efficiency of gas conversion into stars, preventing too rapid depletion of the raw materials needed for long-term galactic evolution. These processes, all initiated when stars preceded structure, helped create the varied galactic ecosystems we observe today. Some galaxies developed stable disks with steady star formation, creating environments where planetary systems could form and evolve without frequent disruption. Others experienced more chaotic evolution, with rapid star formation bursts and frequent galactic mergers, creating less stable conditions. This diversity of galactic environments, established early in cosmic history when stars began shaping emerging structure, created multiple pathways for the potential development of habitable worlds. Some regions might provide more favorable conditions than others, but the widespread distribution of essential elements and the variety of galactic environments increased the overall probability that life-supporting planets would eventually emerge somewhere in the cosmos. The sequence stars first, structure second, thus connects to one of humanity's most profound questions: are we alone in the universe? If the chemical ingredients and physical conditions necessary for life became available very early in cosmic history, before galaxies were fully formed, the potential timeline for life's emergence elsewhere could be much longer than previously thought. Habitable planets might have formed billions of years before Earth, orbiting stars in the first substantial protogalaxies. This perspective reminds us that cosmic evolution is not a uniform process with the same timeline everywhere. Just as structure formation proceeded at different rates in different regions, with some protogalaxies forming hundreds of millions of years before others, the conditions for habitability likely emerged asynchronously across cosmic space. Some regions might have developed habitable environments billions of years before others, creating a vast range of potential timelines for life's emergence. The pattern of stars preceding and shaping structure exemplifies a broader principle about the universe's evolution, that it proceeds not through a single linear path, but through countless parallel developments unfolding at different rates across cosmic space. This non-uniformity, present since the earliest stars began influencing their surroundings, has created the rich diversity of environments we observe today, from dense galaxy clusters to isolated field galaxies, from active galactic nuclei to quiet stellar neighborhoods like our own. Within this diversity, lie multiple potential pathways for the emergence of complexity, different environments where stars, planets, and potentially life could develop along varied evolutionary trajectories. This multiplicity of cosmic possibilities, initiated when stars first preceded structure, represents one of the most profound aspects of our universe's evolution: its capacity to explore many developmental pathways simultaneously, increasing the likelihood that some might lead to conditions capable of supporting conscious observers like ourselves. The story of stars preceding structure thus connects the earliest chapters of cosmic history to the conditions that eventually made our existence possible. It reveals how the universe's very first luminous objects set in motion processes that would, billions of years later, create environments where planets could form, chemistry could diversify, and life could potentially emerge. It demonstrates the profound continuity linking cosmic dawn to the present day, an unbroken chain of cause and effect stretching across nearly 14 billion years of cosmic evolution. How does a universe find its voice? Before words existed, before planets formed, before even galaxies had taken shape, the cosmos began telling its first story. This narrative wasn't inscribed in books or spoken aloud, but written in light, the radiance of the first stars as they pierced the primordial darkness. Light is, in many ways, the universe's original language. It carries information across vast distances and through enormous spans of time. The photons streaming from those first stellar giants encoded details about their temperature, composition, and motion. They recorded the conditions of a universe just emerging from its dark infancy. They transmitted the signature of nuclear fusion occurring for the first time, marking the moment when the cosmos began creating complexity from simplicity. This first cosmic story, told in the language of light, continues reaching us today, though now stretched by the universe's expansion into wavelengths our eyes cannot see. When our most sensitive telescopes detect this ancient radiation, they're receiving the universe's first message, sent across nearly 14 billion years of cosmic time. What makes this initial cosmic narrative so profound is that it marked a fundamental transition, the moment when the universe developed the capacity to remember. Before the first stars, the cosmos existed as a nearly uniform sea of hydrogen and helium, with tiny density variations providing the only meaningful structure. Information density was low, with few distinctions to separate one region from another. But when the first stars ignited, they created localized centers of energy, temperature, and chemical complexity that stood in sharp contrast to their surroundings. They established patterns that could persist and evolve, patterns containing vastly more information than the relatively uniform medium from which they emerged. These patterns weren't random, but governed by physical laws. The light from the first stars told a story of gravity drawing matter together, of quantum mechanics enabling fusion reactions, of nuclear physics building new elements. It recorded how the universe began assembling complexity from fundamental forces and simple ingredients. The storytelling capacity of the first stars extended beyond their direct radiation. The heavy elements they forged, carbon, oxygen, silicon, iron, and more, became a kind of cosmic memory, preserving information about conditions inside their cores. When these stars exploded as supernovae, they scattered these element-encoded memories across space, where they would influence future chapters of cosmic evolution. These chemical signatures created a persistent record, much like written language. Just as human writing allows information to transcend individual lifespans, the elements created by the first stars carried information beyond their brief lives. Astronomers today can read these chemical patterns in ancient stars, deciphering details about cosmic conditions billions of years ago. The first stars also told their story through structure and motion. Their gravitational influence altered the distribution of matter around them, creating patterns that would persist and evolve long after the stars themselves had vanished. Their radiation pressured surrounding gas. Their supernova explosions sent shockwaves racing through space, and their newly formed heavy elements changed how gas could cool and collapse. These effects weren't temporary, but cascaded through cosmic history. The structures initiated by the first stars influenced where subsequent generations would form. The elements they created enabled new types of stellar and planetary systems. The patterns they established in the distribution of matter helped shape the emerging cosmic web of filaments and voids. In this way, the first stars weren't merely brief phenomena, but authors of a continuing cosmic narrative. They established initial conditions and trajectories that would influence all subsequent development. They created a kind of memory in the fabric of the universe itself, patterns that would persist and evolve over billions of years. This perspective on cosmic memory connects to profound questions about information and structure in our universe. How does a cosmos governed by the second law of thermodynamics, which describes increasing entropy or disorder, nevertheless develop complex, ordered structures? How does information persist and accumulate, rather than dissipating into background noise? The first stars offer insights into these questions. While they increased the universe's overall entropy through fusion reactions that converted mass to energy, they simultaneously created localized regions of increased order and complexity. They demonstrated how energy flows can generate and maintain structure, establishing patterns that could persist despite the general tendency toward disorder. The story told by the first stars wasn't predetermined but emerged from the interplay between physical laws and initial conditions. Quantum fluctuations in the universe's earliest moments established slight variations in density that would determine where the first stars could form. These random seeds, amplified by gravity over hundreds of millions of years, led to the particular pattern of first illuminatione, pattern that could have been different if those initial fluctuations had been distributed differently. This blend of lawfulness and contingency characterizes cosmic evolution at all scales. The universe develops according to consistent physical principles, yet the specific forms that emerge depend on particular conditions and histories. The first stars exemplified this duality. Their formation and evolution followed universal physical laws, but their specific distribution and characteristics were shaped by the contingent history of density fluctuations in their region of space. The narrative told by the first stars was also fundamentally creative. Through nuclear fusion, they generated elements that had never before existed in significant quantities. Carbon, oxygen, and heavier elements emerged for the first time, creating new possibilities for chemical complexity. The universe's vocabulary expanded, enabling new types of structures and systems that would have been impossible in the initial hydrogen-helium environment. This creativity established a pattern that would continue throughout cosmic history. Each generation of stars built upon the achievements of its predecessors, creating new elements and enabling new types of chemical and eventually biological complexity. The periodic table itself represents a kind of cosmic story, with each element marking a chapter in the universe's ongoing creative development. As the first stellar generation lived and died, their individual stories merged into collective patterns. Radiation from many stars ionized vast regions of intergalactic hydrogen. Heavy elements from numerous supernovae mixed together, enriching the medium from which future stars would form. Gravitational influences combined to shape the distribution of matter on increasingly large scales. This emergence of collective patterns from individual phenomena exemplifies another fundamental aspect of cosmic storytelling, the development of higher-order structures with properties beyond those of their components. The ionized regions around individual stars merged into the cosmic reionization that transformed the universe's physical state. The elements from individual supernovae combined into the chemical enrichment that would enable planetary systems and eventually life. As the first protogalaxies began forming from these collective influences, the cosmic narrative gained new dimensions. These early galactic systems represented new characters in the universe's story, collective entities with emergent properties beyond those of individual stars. They developed internal structures, rotation patterns, and evolutionary trajectories that would shape subsequent chapters of cosmic history. The James Webb Space Telescope is now allowing us to observe these ancient protogalaxies directly, revealing systems that formed just a few 100 million years after the Big Bang. These observations expand our understanding of the cosmic narrative, showing how quickly complexity emerged from the relatively simple early universe and how structure began organizing at progressively larger scales. What makes the story told by the first stars and early galaxies particularly significant is that it continues resonating in our present-day cosmos. We exist within a universe shaped by the patterns established during cosmic dawn. The elements in our bodies were forged through stellar processes that began with the first generation of stars. The structure of our galaxy reflects billions of years of evolution initiated when those first lights began influencing their surroundings. In this sense, The first cosmic story never ended, but continues unfolding, with each generation building upon the achievements of its predecessors. The universe's initial creative burst, the formation of the first stars, established patterns of development that would eventually lead to galaxies, planetary systems, and ultimately, conscious beings capable of contemplating their own cosmic origins. This continuity doesn't mean cosmic evolution is simply repetitive. Each era introduces new elements and possibilities. The first stars formed from pristine hydrogen and helium in a universe without existing structure. The second generation formed in environments already influenced by their predecessors. Modern stars form within complex galactic ecosystems shaped by billions of years of evolution. Similarly, the types of structures possible in the universe have diversified over time. The first stars and protostructures were relatively simple systems. As cosmic evolution continued, more complex forms emerged: spiral galaxies with differentiated components, planetary systems with specialized worlds, and eventually, living systems capable of self-replication and adaptation. This progressive diversification represents another key aspect of the cosmic story: its movement from uniformity toward variety, from simplicity toward complexity. The first stars initiated this journey, creating the first substantial contrasts in a universe that had previously been nearly homogeneous. They established the first significant energy gradients, chemical distinctions, and structural variations. The light from these first stellar beacons carried the signature of this emerging complexity. It recorded how uniform gas clouds had collapsed into distinct objects with internal structures and differentiated compositions. It documented the first substantial energy processing in the post-recombination universe, the conversion of gravitational potential and nuclear binding energy into radiation and motion. This light also carried information about time, about processes unfolding at different rates across cosmic history. The momentary flash of a supernova conveyed a different temporal story than the steady shine of a main sequence star. The expanding bubble of ionized hydrogen around a stellar source marked time's passage at the speed of light. These varying timescales created a cosmic rhythm, a temporal dimension to the universe's first narrative. As this ancient light continues traveling through the expanding universe, it carries these stories across vast distances, connecting regions that would otherwise remain causally separated. A photon from one of the first stars could influence gas clouds hundreds of millions of light years away, potentially triggering new episodes of structure formation. In this way, light became not just the carrier of cosmic information, but an active participant in the universe's ongoing development. The first cosmic story thus established patterns that would characterize all subsequent cosmic narratives: creativity emerging from fundamental forces, information preserved in persistent structures, complexity developing from simplicity, and connections forming across vast distances through light and gravity. This perspective offers insights into how meaning emerged in our universe. Before conscious interpreters existed, the cosmos was already creating patterns that contained significant information differences that made a difference, variations that would influence future development. The first stars established distinctions that mattered for everything that would follow, creating a kind of proto-meaning through their effects on subsequent cosmic evolution. The universe's first story also exemplifies how narratives themselves emerge from physical processes. The light from the first stars didn't just record random events, but sequences with causal connections and temporal development. Gas collapsed under gravity, ignited through nuclear fusion, processed elements through stellar evolution, and scattered new materials through explosive deaths. These connected processes created a narrative structure with beginning, middle, and end, a cosmic story with its own internal logic. This narrative quality extends beyond individual stars to their collective influences. The transition from the Dark Ages to cosmic dawn, the progress of reionization across intergalactic space, the gradual chemical enrichment of the cosmic medium, these developments unfolded as coherent processes with direction and consequence. They tell a story of transformation, of a universe developing new capabilities and characteristics over time. What distinguishes this cosmic storytelling from human narratives is its distributed, emergent nature. No single entity designed or orchestrated these developments. They emerged from the interaction of physical laws operating across cosmic scales, yet they display narrative qualities: coherence, development, and consequence that we typically associate with authored stories. This emergent narrative quality appears throughout natural history, from the evolution of stars to the development of living systems. Patterns emerge, persist, and influence subsequent events without requiring conscious direction. Information accumulates in structures that outlast their origins. Complexity builds upon previous achievements rather than arising spontaneously at each stage. The first stars exemplify these characteristics of natural storytelling. They weren't designed or planned, but emerged from the interaction of gravity, nuclear physics, and initial conditions. Yet their formation, evolution, and deaths unfolded as coherent processes with far-reaching consequences. They became characters in a cosmic drama that continues influencing our universe billions of years later. This perspective challenges sharp distinctions between natural processes and meaning-making. The universe doesn't merely provide raw material for human storytelling, but generates its own narratives through physical processes that create, preserve, and transmit information. The first stars weren't just objects, but participants in a cosmic story that continues unfolding to the present day. Modern astronomy allows us to recover aspects of this original cosmic narrative. When we observe ancient light from distant galaxies, map the distribution of elements across space, or simulate the conditions of the early universe, we're reconstructing chapters in the story that began with the first stars. We're reconnecting with the universe's earliest attempts to create complexity and structure, develop a cosmic memory that could persist through time. This scientific reconstruction itself represents a new dimension in cosmic storytelling. Through systematic observation and analysis, conscious beings can now recover information about events that occurred billions of years before their emergence. The universe has developed the capacity not just to create and preserve information, but to systematically interpret its own history. In this sense, human consciousness and science represent new capabilities in an ongoing cosmic process, rather than phenomena entirely distinct from natural development. We are, in a very real sense, the universe reflecting on its own history, expressions of a cosmos that has evolved the capacity to reconstruct its own narrative from fragmentary evidence preserved across billions of years. The first stars thus connect to profound questions about meaning, memory, and consciousness in our universe. They demonstrate how information can be created and preserved through physical processes. They show how patterns can develop that influence subsequent cosmic evolution, and they reveal how a universe governed by physical laws can nevertheless generate narrative structures with temporal depth and causal significance. When we contemplate the light from cosmic dawn, we're engaging with the universe's first attempt to tell its own story, to create patterns that would persist, to establish differences that would matter, to develop complexity that could evolve. We're reconnecting with a cosmic narrative that began long before conscious interpreters existed, but that would eventually lead to beings capable of reconstructing and comprehending their own origins. This perspective doesn't require mystical thinking or anthropomorphizing the cosmos. It simply recognizes that processes like information preservation, pattern formation, and temporal development qualities we associate with storytelling emerge naturally in a universe governed by the physical laws we observe. The first stars exemplify these emergent narrative qualities, creating and transmitting information that continues influencing cosmic development billions of years later. The story told by the first stars wasn't a final or complete account, but the opening chapter in an ongoing cosmic narrative. It established patterns and possibilities that subsequent developments would elaborate and transform. It created conditions necessary for new types of structures and systems, while setting constraints on how they could form and evolve. In many ways, the first cosmic story resembles the opening moves in a game of chess. These initial developments don't determine the entire subsequent course, but establish framework and possibilities. They create a situation from which countless different futures might emerge, each building upon what came before while introducing new patterns and relationships. What makes the cosmic narrative particularly fascinating is its multi-scale nature. Processes operating at subatomic scales inside stellar cores connect to the distribution of galaxies across billions of light years. Events lasting fractions of a second influence, developments spanning billions of years. The cosmic story unfolds simultaneously across vastly different dimensions of size and time, with patterns at each scale influencing those at others. The first stars exemplify this multi-scale storytelling. Nuclear reactions in their cores created elements that would eventually form planets and living organisms. Their collective radiation influenced the development of structure across millions of light years. Their brief individual lives initiated patterns that would persist through billions of years of cosmic evolution. They connected the microphysics of fundamental particles to the macrophysics of emerging cosmic structure. This interconnection across scales distinguishes cosmic evolution from many human narratives, which typically focus on particular levels of organization. The universe doesn't compartmentalize its development, but creates through the continuous interaction of processes operating across all scales simultaneously. The first stars weren't isolated phenomena, but nexus points where multiple scales of physical processes converged and influenced each other. The multi-layered cosmic story also features varying degrees of contingency and necessity. Some aspects appear inevitable, given the laws of physics. Hydrogen will fuse to helium under sufficient pressure and temperature, releasing energy in the process. Others depend on particular conditions, and history's the specific distribution of the first stars resulted from the pattern of quantum fluctuations amplified during cosmic inflation. This interplay between lawfulness and contingency creates a cosmic narrative neither entirely random nor completely predetermined. Given the laws of physics and initial conditions of our universe, stars would inevitably form, but their specific patterns, timing, and characteristics depended on particular cosmic histories. The universe tells its story through the interaction of universal principles with specific circumstances, creating a narrative that combines predictability with novelty. The first stars embodied this blend of necessity and contingency. Their formation represented an inevitable outcome of gravity acting on density variations in expanding space. Yet their specific distribution, masses, and lifespans depended on particular conditions in their formation environments. They demonstrated how universal physical laws could produce unique outcomes when operating in different contexts. This perspective offers insights into the relationship between cosmic patterns and the emergence of life. Living systems represent another form of cosmic storytelling, entities that preserve and transmit information through molecular structures rather than elemental abundances or radiation patterns. They develop through the interaction of universal principles, chemistry, thermodynamics, with particular environmental conditions and histories. The possibility of life emerging somewhere in the cosmos was established when the first stars created carbon, oxygen, nitrogen, and other biologically relevant elements. They wrote these chemical possibilities into the cosmic narrative, enabling forms of complexity and information processing that wouldn't have been possible in the hydrogen-helium universe that preceded them. In this sense, life represents a continuation of patterns established by the first stars, the emergence of complexity from simplicity, the preservation of information in persistent structures, the development of systems that can respond to and modify their environments. The cosmic story that began with the first points of light continues through living systems, which represent new mechanisms for generating, preserving, and processing information. Consciousness itself can be viewed through this lens as another chapter in cosmic storytelling, a mechanism through which the universe can reconstruct its own history and contemplate alternative futures. When we study the first stars and the emergence of cosmic structure, we're participating in a universe that has developed the capacity to reflect on its own development, to recover information about its earliest epochs from evidence preserved across billions of years. This doesn't make human consciousness the purpose or goal of cosmic evolution, but it does highlight remarkable continuities between processes operating at different levels of organization. The preservation of information through chemical elements scattered by the first supernovae connects to the preservation of information through neural patterns or written language. The emergence of structure from simple physical laws connects to the emergence of thought from neural interactions. The story that began when the first stars illuminated cosmic darkness continues unfolding through every level of organization that has emerged since galaxies, planetary systems, living organisms, conscious minds, cultures, and technologies. Each represents a new mechanism for generating, preserving, and transmitting information, a new chapter in a cosmic narrative that began nearly 14 billion years ago. This continuity doesn't diminish the distinctiveness of different phenomena, but reveals how they participate in shared patterns of development. It suggests that human meaning-making isn't separate from cosmic processes, but represents new expressions of tendencies present since the first stars began converting simplicity into complexity, uniformity into structure, potential into actuality. When we gaze at the night sky, we're connecting with a story that began when the first stars pierced the cosmic darkness. The light reaching our eyes has traversed vast distances and times, carrying information about processes that shaped our universe long before our planet formed. We're reading the latest chapters in a narrative that began at cosmic dawn, written in the language of light that continues illuminating our understanding of this remarkable universe we inhabit. The story that began with the first stars reminds us of our deep connection to cosmic history. The iron in our blood, the calcium in our bones, the carbon in our cell soul, these elements were first forged in stellar cores, beginning with the first generation of stars that transformed the primordial hydrogen and helium into more complex forms. We are, in a very real sense, made from stardust participants in a cosmic story that began billions of years before our emergence. This perspective doesn't just connect us to the past, but extends our vision toward possible futures. The cosmic narrative that began with the first stars continues evolving, with new chapters yet to be written. The universe that developed complexity from simplicity, structure from uniformity, consciousness from matter may still have remarkable transitions ahead, developments as transformative as the emergence of the first stars from primordial darkness. In this unfolding story, we occupy a privileged positionable to reconstruct the cosmos's past development while contemplating the possibilities for its future. We can trace the narrative from its earliest chapters at cosmic dawn to the present moment, identifying patterns and principles that have shaped evolution across billions of years. And we can consider how these patterns might continue developing, how the creativity evident since the first stars might express itself in forms we cannot yet imagine. The cosmic story that began when light first pierced the darkness thus extends in both directions, backward toward origins and forward toward possibilities. It connects us to a universe that has been generating complexity, preserving information, and developing new capabilities since its earliest epochs. And it reminds us that we are not just observers of this cosmic narrative, but participants in its continuing evolution, inheritors of processes that began with the first stars and contributors to chapters yet to be written. This perspective offers a profound integration of scientific understanding with existential meaning. The factual account of cosmic evolution from first stars to conscious beings carries implications for how we understand our place in the universe. We are not accidental visitors to an indifferent cosmos, but expressions of tendencies present since cosmic dawn, a universe that has been generating complexity, structure, and new capabilities throughout its history. The light from the first stars thus tells a story that continues illuminating our understanding of both cosmic history and human significance. It reveals a universe characterized not just by expansion and entropy, but by the emergence of complexity and meaning. It connects us to processes that have been unfolding since the first nuclear fires ignited in the cosmic darkness. And it suggests that we participate in a creative development that began with the universe's first attempt to tell its own story, a narrative written in light that continues guiding our understanding of who we are and what we might become. The story that began at cosmic dawn is, in many ways, the greatest narrative ever told, a tale spanning nearly 14 billion years and trillions of miles, encompassing phenomena from subatomic particles to superclusters of galaxies. It's a story with countless characters, from the first massive stars to the billions of stellar systems in our Milky Way alone. It's a narrative of transformation, creativity, and emergency universe developing new capabilities and forms throughout its long history. What distinguishes this cosmic story from human narratives is not just its scale, but its distributed, emergent nature. It unfolds not through the intentions of a single author, but through the interaction of physical processes operating across all scales simultaneously. It develops through both lawful regularities and contingent histories, creating patterns that could not have been precisely predicted at the outset, yet remain comprehensible through their underlying principles. The first stars began telling this remarkable story when they converted the potential of gravity and nuclear binding energy into the actuality of light and heavy elements. They initiated patterns of complexity, structure, and information transmission that would eventually lead to galaxies, planetary systems, and life. They demonstrated how a universe governed by physical laws could nevertheless generate novelty, creativity, and development. As we continue exploring cosmic dawn with increasingly powerful observational and computational tools, we recover more chapters of this original cosmic narrative. We trace how the first points of light influenced their surroundings, how they contributed to the emergence of larger structures, how they established patterns that would shape all subsequent cosmic evolution. We reconnect with the beginning of a story that continues unfolding to the present day, a narrative written in light that began when the universe first found its voice in the radiation of newborn stars. This cosmic story continues resonating across space and time, carried by light that connects distant regions and epochs. It's preserved in the abundance patterns of elements, in the distribution of galaxies across cosmic scales, in the chemistry that enables life on at least one planet orbiting an ordinary star. It's a narrative we can read in the night sky, in laboratory experiments, in the composition of our own bodies. And it's a story that continues unfolding, with new chapters emerging through processes that have been operating since the first stars illuminated the cosmic darkness. In this ongoing cosmic narrative, we occupy a unique positionable to reconstruct the universe's history from evidence preserved across billions of years, while participating in its continuing evolution. We are both readers and writers of the cosmic story, inheritors of processes that began at cosmic dawn, and contributors to developments that may extend far into the future. We are the universe reflecting on its own history, expressions of a cosmos that has evolved the capacity to contemplate its origins and possibilities. The story that began when the first stars illuminated primordial darkness thus continues through our efforts to understand cosmic evolution and our decisions about how to participate in its ongoing development. It connects us to the deepest patterns of a creative cosmos, while challenging us to consider what new chapters we might contribute to this remarkable narrative that began nearly 14 billion years ago with the universe's first to attempt to tell its own story. The first stars burned quickly, then disappeared, but they left behind everything. As we've journeyed through cosmic history tonight, we've traced the remarkable story of the universe's first luminaries, those massive, brilliant giants that emerged from darkness and transformed the cosmos forever. Though they vanished billions of years before our own solar system formed, their legacy surrounds us in every aspect of our universe. When those first stars exhausted their nuclear fuel after just a few million years of brilliant existence, they didn't truly end, they transformed. Through spectacular supernova explosions, they scattered their newly forged elements across space: carbon, oxygen, silicon, iron elements that had never existed in significant quantities before. These stellar alchemists converted the simple hydrogen and helium of the primordial universe into the complex elements necessary for planets and eventually life. Look around you. The calcium in your bones, the iron in your blood, the oxygen you breathe, all these elements were created inside stars. And the very first batches were forged in those ancient population 3 giants that illuminated cosmic dawn. Their deaths weren't endings, but beginnings, the critical first step in a process of cosmic enrichment that would eventually enable our existence. The light from those first stars did more than merely illuminate darkness. It fundamentally altered the physics governing cosmic evolution. Ultraviolet radiation from these stellar behemoths stripped electrons from hydrogen atoms, creating expanding bubbles of ionized plasma. As these bubbles grew and merged, they transformed the universe's physical state, making it transparent to certain wavelengths of light and changing how matter could collapse to form future structures. This process, cosmic reionization, represented one of the last major phase transitions our universe has undergone. It changed the environment in which all subsequent cosmic evolution would unfold, influencing everything from the formation of galaxies to the efficiency of star formation to the eventual emergence of planetary systems. The universe before reionization and after were fundamentally different places, with different physics governing structure formation. The explosive deaths of the first stars sent shock waves racing through primordial gas, compressing some regions while heating and dispersing others. These mechanical effects, combined with the chemical enrichment from their supernovae, created a patchwork of environments with different star-forming capabilities. Some regions could now cool and collapse more efficiently, accelerating structure formation. Others were temporarily heated beyond the threshold where gravity could overcome thermal pressure. This pattern of alternating suppression and enhancement established a self-regulating system that guided subsequent cosmic evolution. Rather than proceeding uniformly across space, structure formation became clustered and episodic concentrated in regions with the right conditions for gas collapse. This pattern helped shape the cosmic web of filaments, nodes, and voids that characterizes our universe's large-scale structure today. The first stars also helped establish the foundations of galactic architecture. As more stars formed around the initial pioneers, their combined gravitational attraction drew in additional gas along cosmic filaments. Their light, heat, and explosive energy influenced where and how this gas could collapse to form new stars. They began establishing feedback loops between stellar activity and gas dynamics that would become central to galaxy evolution. These processes guided the transition from isolated stars to the first proto-galaxies, irregular, chaotic collections of stars embedded in gas clouds. These primitive galactic systems formed primarily at the intersections of cosmic filaments, where matter density was highest, and the first stars had already established footholds. They contained both population 3 stars formed from pristine gas and population 2 stars formed from slightly enriched material. As these protogalaxies merged and grew, they developed more complex internal structures. Gas settled into rotating disks due to conservation of angular momentum. Stars formed within these disks inherited their orbital motion, creating the first primitive spiral patterns. Other systems experienced more chaotic mergers that scrambled stellar orbits, creating spheroidal structures that would evolve into elliptical galaxies. By about 1 billion years after the Big Bang, many of the essential features of the galaxy population were established. There were massive galaxies and dwarf galaxies. There were systems dominated by ordered rotation and systems with more random stellar motions. There were galaxies actively forming stars and galaxies where star formation had been temporarily suppressed by feedback or gas depletion. The universe had completed its transition from isolated stars to a complex ecosystem of interacting galaxies, setting the stage for billions of years of continued evolution that would eventually produce the rich variety of galaxies we observe today, including our own Milky Way, within which our solar system would form about 4.6 billion years ago. The story of the first stars connects directly to our own existence. Every atom in your body heavier than lithium was created inside a star, then scattered across space when that star died. The first generation of stars began this process of cosmic enrichment, creating the initial batches of heavy elements that would eventually find their way into planets and living beings. The oxygen molecules you're breathing right now contain atoms that were first forged inside stars, possibly including some from that very first stellar generation. The carbon atoms forming the complex organic molecules in your cells continue a lineage that began when the first massive stars created carbon through triple alpha fusion of helium nuclei. The iron in your blood carries the signature of stellar explosions that occurred billions of years before our planet formed. In this very real sense, we are children of the stars, not just poetically but literally. The universe required stellar alchemy to create the elements necessary for our existence. And that alchemy began with the first stars, those primordial giants that transformed the simple hydrogen-helium universe into one capable of chemical complexity. The legacy of the first stars extends beyond chemistry to the very structure of our cosmic environment. Our Milky Way galaxy formed through the merger of smaller proto-galaxies, each influenced by stars that formed during or shortly after cosmic dawn. The distribution of gas, stars, and dark matter in our galactic neighborhood reflects patterns established when the first stars began shaping their surroundings. Even the orbit of our solar system around the galactic center taking about 230 million years to complete follows paths influenced by the distribution of matter established during galactic assembly, a process initiated when the first stars helped guide matter flows along cosmic filaments. The first stars also connect to profound questions about our place in the cosmic timeline. They remind us that the universe has been developing complexity for billions of years before our emergence. The conditions necessary for planets like Earth with the right chemical compositions to support life required multiple generations of stellar processing, beginning with those first luminaries. This perspective places us not at the beginning of cosmic history, but well into its development. The universe had already experienced several major transitions, from inflation to nucleosynthesis, to recombination to the formation of the first stars, to the assembly of galaxies, before the material that would form our solar system had been gathered and processed through multiple stellar generations. Yet we're also nowhere near the end of cosmic possibilities. The universe that developed from simplicity to complexity, from darkness to light, from primordial elements to living beings, likely has remarkable transitions still ahead. Just as the first stars transformed a universe of hydrogen and helium into one capable of forming planets and life, future cosmic evolution may enable forms of complexity we cannot yet imagine. What makes humans unique in this ongoing cosmic story is our capacity to reconstruct the universe's history from evidence preserved across billions of years. We can trace our cosmic lineage back to those first stellar beacons, understanding how their light, elements, and structural influences set the stage for everything that followed. We can read the story that began when the universe first found its voice in the radiation of newborn stars. This scientific perspective connects us to deep time in ways our ancestors could never have imagined. We now know that when we look up at the night sky, we're seeing light that has traveled across vast cosmic distances and time periods. The most distant objects visible with our most powerful telescopes appear as they were just a few 100 million years after the Big Bang, approaching the era when the first stars illuminated cosmic darkness. The Webb Space Telescope is pushing this observational horizon ever closer to cosmic dawn, revealing galaxies that formed when the universe was less than 400 million years old. These observations connect us more directly to the universe's formative periods, showing how quickly structure emerged from the relatively uniform early cosmos and how the first generations of stars influenced this development. As our observational and computational capabilities continue advancing, we edge closer to witnessing the moment when the universe's first story began, when the initial stellar beacons pierced the cosmic darkness. This quest to understand our deepest cosmic origins represents one of humanity's greatest intellectual adventures, connecting us to processes that unfolded billions of years before our species evolved, but that were nevertheless crucial for our eventual emergence. Tonight, as you lie beneath the stars, consider that you're looking at the distant descendants of those first luminaries. The stars visible in our night sky belong to much later generations, formed from gas already enriched by multiple cycles of stellar birth and death. But they continue processes initiated at cosmic dawn: nuclear fusion converting hydrogen to helium, radiation transporting energy across space, stellar winds, and eventual deaths that will further enrich the interstellar medium. The cosmos above you is filled with billions of galaxies, each containing billions of stars, all participating in a grand cycle of cosmic evolution that began when the first lights appeared in the primordial darkness. The elements in your body were forged in stellar cores and scattered by stellar explosions, beginning with that first generation. The patterns of cosmic structure surrounding us, from our solar system to our galaxy to the larger cosmic web, bear the influence of processes initiated when stars first preceded and shaped emerging cosmic structure. Sleep now, beneath stars born from ashes scattered by their ancient predecessors. Dream of the light that came before form, before time had a name. The universe's first story continues unfolding around and within you, connecting you to processes that have been operating since cosmic dawn. The first stars burned briefly but brilliantly, transforming darkness into light, simplicity into complexity, potential into actuality. Though they vanished long ago, their legacy continues in every element heavier than lithium, in the structure of galaxies, and indeed, in our own existence. The story that began when the first stars illuminated primordial darkness continues through us beings composed of star-forged elements, inhabiting a planet orbiting a later generation star, capable of reconstructing cosmic history from evidence preserved across billions of years. We are not just observers of this cosmic narrative, but participants in its continuing evolution, inheritors of processes that began with the first stars and contributors to chapters yet to be written. As you drift towards sleep, consider that you're not separate from this cosmic story, but an integral part of Itar, remarkable expression of a universe that has been developing complexity and new capabilities throughout its long history. The light from those first stars helped shape a cosmos that would eventually enable your existence. Their elements form your body. Their influence on cosmic structure created environments where planets could form and life could emerge. In this profound sense, we carry the legacy of the first stars within us. We are children of cosmic light, descendants of processes set in motion when the universe first began creating complexity from simplicity, form from formlessness, structure from near uniformity. The story that began at cosmic dawn continues through our existence and our quest to understand our deepest origins. Rest now beneath the cosmic canopy that has witnessed the universe's long evolution from first stars to conscious beings. Dream of the light that first transformed darkness into the structured cosmos we inhabit, and perhaps feel a deeper connection to the night sky, knowing that you're part of an unbroken chain of cause and effect stretching back to cosmic dawner, living legacy of stars that shone billions of years before Earth formed, but whose influence continues in every atom of your being.